For many years, scientists thought that intelligent life, like humans, was a rare and lucky accident in the vast universe. They believed that everything had to line up just right for us to exist, like winning the cosmic lottery. But now, a brand new study is shaking things up. It suggests that the rise of intelligent beings like us wasn't some unlikely miracle. Instead, it may have been a natural result of how Earth slowly changed and developed over time. In other words, maybe life like ours was meant to happen all along. Are we truly intelligent enough to grasp the full truth of who we are, where we come from, and what it all means? Before we begin this video, let us know where in the world you're watching from, and what time it is for you right now. Post it in the comments below, and settle in for a fascinating journey. For a very long time, many scientists believed that humans were a kind of cosmic miracle, a rare event in the universe that happened only because of an extraordinary stroke of luck. According to this way of thinking, intelligent life like ours wasn't just unusual, it was nearly impossible. It was as if the universe had to roll a trillion-sided dice and land on exactly the right number for thinking, talking, tool-using creatures like us to appear. But now, some scientists are beginning to question that idea. A new scientific model suggests something radically different, that the rise of intelligent beings like humans was not some lucky accident, but the natural result of how planets like Earth evolve over time. This model was developed by a group of researchers from Pennsylvania State University, often called Penn State for short. Their research challenges what is known as the hard steps theory, an older idea that claims intelligent life can only arise if a long list of highly unlikely things all happen in just the right way. That theory sees humanity as the outcome of an almost impossible journey, filled with difficult obstacles, each one unlikely to be overcome. But the team at Penn State has a different view. They argue that life, especially intelligent life, isn't the outcome of cosmic luck. It's the result of natural forces working together over billions of years. According to their findings, the development of intelligence could be common across the universe. In other words, if the conditions are right, the rise of creatures that can think, build, dream, and ask questions about the cosmos might actually be expected, not exceptional. Let's dive deeper into this powerful idea, explore how it compares to older theories, and understand what it might mean for our place in the universe. Before we can fully understand the new model, it helps to take a closer look at the older idea it challenges, the hard steps theory. This theory was first introduced by scientists who looked at how life evolved on Earth. They noticed that it took a very long time, almost 4 billion years, for intelligent life to appear. That's nearly the entire age of the Earth itself, which is about 4.5 billion years old. According to the hard steps theory, that long timeline is a clue. It suggests that there were a number of crucial events in Earth's history, big changes in biology or chemistry, that were extremely unlikely to happen. These were the hard steps. Each one was so rare and so difficult that it took millions or even hundreds of millions of years for evolution to stumble across it. Some examples include the first appearance of simple cells or prokaryotes, the evolution of complex cells or eukaryotes, the development of multicellular life, the rise of nervous systems and brains, the eventual emergence of tool-using intelligent species like humans. Under this model, if even one of these steps had failed to happen, intelligent life might never have come into being. And since each step was supposedly so unlikely, the theory suggests that it's extremely rare for life to go all the way from microbes to minds, even on other planets. That's why the hard steps theory paints a lonely picture of the universe. We might be one of very few, or possibly the only intelligent civilizations that has ever existed. Now let's look at the new idea from Penn State, which turns this thinking on its head. The scientists behind this new model argue that instead of being rare and unlikely, the rise of intelligence might be a built-in part of how some planets change and develop over time. If a planet has the right conditions, a stable climate, liquid water, the right mix of chemicals and enough time, then life will not only appear, but eventually grow smarter and more complex. In this view, intelligence is not the result of winning the cosmic lottery. It's more like the final stage of a long natural process, similar to how a caterpillar becomes a butterfly, or how a seed becomes a tree. Their model is based on the idea of planetary evolution, the belief that just as life evolves, so do planets. Over billions of years, a planet's surface, atmosphere, and ecosystems slowly change. These changes affect the life that exists on the planet. Life, in turn, affects the planet as well, creating a feedback loop that pushes both toward greater complexity. Eventually, given enough time and stability, these changes could lead to the rise of creatures with intelligence, beings who can observe the universe, build tools, share knowledge, and even send messages into space. You might be wondering, why does any of this matter? It matters because this new model dramatically changes how we think about life in the universe. If intelligence is a common outcome of planetary evolution, then the universe could be teeming with civilizations, some younger than ours, some much older, and all shaped by their own unique environments. It also changes how we search for alien life. Right now, our searches often assume that intelligent life is rare. We use giant telescopes to scan distant stars, looking for faint radio signals or signs of technology. But if intelligence is more common than we thought, maybe we're not looking in the right places, or maybe we're not listening in the right way. This idea also changes how we see ourselves. If intelligence is a natural outcome of evolution, then being human is not about being special or chosen. Instead, it means we are part of a much bigger cosmic story, one that could be playing out on millions or even billions of other worlds. Let's break down the Penn State model in simpler terms. The researchers at Penn State used mathematical simulations and evolutionary theory to build a new picture of how life might develop on a planet like Earth. Instead of focusing on specific hard steps, they looked at how different environmental pressures, like climate, geology, and energy sources, might guide life toward intelligence. Their model assumes that life starts simply, as it likely did on Earth about 3.5 to 4 billion years ago. Over time, life becomes more complex, adapting to the changing planet. These changes might include the rise of oxygen in the atmosphere, the shifting of continents and formation of oceans, changes in temperature and light, the movement of species into new environments. All of these forces create new challenges and new opportunities. According to the model, intelligence is one of the most powerful tools life can evolve to deal with these challenges. So, once life starts on a planet, there's a good chance that intelligence will follow, if the planet stays habitable long enough. The Penn State model is different from older theories in a few key ways. Firstly, it focuses on conditions, not coincidences. The hard steps theory says that life is rare because too many coincidences have to line up just right. But the new model says that what really matters is the overall environment of the planet, things like temperature, atmosphere, and chemical composition. If those conditions are stable and supportive, life can thrive and evolve naturally. It's not about luck, it's about time and biology. Secondly, it sees evolution as a driving force. In the hard steps theory, evolution is treated like a series of random dice rolls. But in the new model, evolution is a guided process, shaped by the environment. Life adapts to survive, and that adaptation drives complexity, eventually leading to intelligence. Thirdly, it suggests life might be common, not rare. This is the biggest difference. If the new model is right, then the universe might be filled with planets that went through the same kinds of changes Earth did. That means intelligent life might not be a 1 in a trillion accident. It might be a regular outcome of planetary evolution. This theory has big implications for how we search for life beyond Earth. If intelligent life is common, then we need to rethink where and how we look for it. Instead of only focusing on finding radio signals or scanning nearby stars, we might also want to look for biosignatures in planetary atmospheres, signs of life's chemical footprints, search for techno signatures, evidence of technology, like city lights or pollution. Study exoplanets, planets outside our solar system that have Earth-like conditions and long histories of stability. There are now thousands of known exoplanets, and that number is growing every year. Some of them may be billions of years old. If the Penn State model is right, a good number of them might be home to intelligent life, or at least to life that is on its way to becoming intelligent. Let's imagine for a moment what this might mean. Somewhere out there, on a planet circling a distant star, creatures may be looking up at their sky, wondering if they're alone, just like we do. They may be building tools, telling stories, asking questions, and dreaming of space. Maybe they've developed their own science and technology. Maybe they've sent messages into the universe. Or maybe, like us, they're still trying to figure out how to listen. The Penn State model invites us to see the universe not as a vast empty space, but as a garden full of growing minds, some just beginning to bloom, others ancient and wise. This idea doesn't just affect how we see the universe, it also affects how we see ourselves. If intelligence is a natural step in evolution, then being human isn't just about being lucky. It's about being part of a process that has played out across time and space, a process that might be woven into the fabric of life itself. It also reminds us that with intelligence comes responsibility. If other civilizations exist, we are part of a broader community of minds, one we have not yet met, but one we may someday join. And if we are alone, then we carry an even greater duty, to preserve life, to explore the stars, and to keep asking the big questions that only intelligent beings can ask. The Penn State model is still a new idea, and like all scientific theories, it will need to be tested and debated. Other scientists will try to find evidence that supports or challenges it. New discoveries in astronomy, biology, and planetary science will help us understand more about how life begins and how it changes. But already, this model is opening the door to a new way of thinking about life in the universe, one that's more hopeful, more inclusive, and more exciting. Humanity may not be some rare exception in the cosmos. According to a new scientific model developed by researchers at Pennsylvania State University, intelligent life might be the expected result of how planets like Earth evolve. This idea challenges the old belief that intelligent life is almost impossibly rare. Instead, it offers a bold new vision, one in which intelligence is a natural, even predictable outcome of life adapting to its environment over time. And if that's true, then the stars above us may not be silent forever. Somewhere out there, across the vast darkness of space, there may be other beings not so different from us waiting to be found. On February the 14th, in the year 2025, a groundbreaking scientific paper was published in the well-respected journal Science Advances. This paper, written by a team of researchers from Pennsylvania State University, has started to change the way scientists think about life, not just on Earth, but throughout the entire universe. One of the co-authors of this new study is Professor Jennifer McCalady, a geoscientist at Penn State. She explained the significance of the discovery in simple but powerful words. This is a significant shift in how we think about the history of life. It suggests that the evolution of complex life may be less about luck and more about the interplay between life and its environment. This idea, that the emergence of intelligent life like humans might not be a fluke or a cosmic accident, opens up an exciting new path for science. It makes us ask bigger, deeper questions. Is humanity a rare miracle, or the natural result of planetary evolution? Could there be other intelligent civilizations out there, developing on distant worlds just like we did? What does this say about our own place in the vast universe? Let's explore the science, the history of this idea, and how it could change everything we think we know. To fully appreciate the new theory, we need to understand the old one. Back in 1983, a brilliant theoretical physicist named Brandon Carter came up with a concept known as the hard steps model. This model was built on the idea that certain steps in the evolution of intelligent life are extremely difficult. So difficult, in fact, that they might happen only once in the entire history of a planet. Here's the basic logic. The Earth has existed for around 4.5 billion years. Our Sun has an estimated total lifetime of about 10 billion years. Humans, meaning modern Homo sapiens, have only been around for roughly 300,000 years. When you compare those numbers, it's clear that intelligent life took a very long time to emerge. According to Carter, this delay wasn't just coincidence. He believed that there were certain hard steps along the evolutionary path that were extremely unlikely to happen quickly, or at all. Imagine trying to win a lottery where the odds are almost impossible. Now imagine needing to win that same impossible lottery 6 or 7 times in a row. That's how Carter saw the emergence of intelligent life. Each of those hard steps had to be overcome, and each was an unlikely event. Some possible examples of these hard steps might include the origin of life itself from non-living chemicals, the appearance of complex single-celled organisms, the leap to multicelled life, the development of sexual reproduction, the rise of intelligent brains capable of thought and language. If Carter was right, then intelligent beings like us are the result of an incredibly rare chain of miracles. And if that's true, the chances of finding other intelligent life in the universe are very, very low. This theory has been widely accepted for decades. It paints a lonely picture of the universe, a beautiful but quiet place, where humanity might be the only voice that ever learned to speak. But now, a new scientific model is offering a different vision. The Penn State study challenges Carter's old idea with a fresh perspective, one rooted in how life and its environment interact over time. According to this new model, the emergence of complex and intelligent life is not simply the result of a few unlikely, hard steps. Instead, it may be the natural and even expected result of how life shapes and is shaped by the planet it lives on. This idea draws on a growing body of evidence from fields like astrobiology, which studies life in the universe, geoscience, which examines Earth's physical systems, evolutionary biology, which looks at how living things change over time. What all these fields are starting to show is that life and its environment are deeply connected. They're not separate systems, they co-evolve together. The presence of life changes the planet, and those planetary changes in turn influence how life continues to evolve. Take oxygen, for example. About 2.5 billion years ago, simple bacteria began producing oxygen as a waste product through a process called photosynthesis. Over time, this oxygen built up in Earth's atmosphere, completely transforming the planet. This event, known as the Great Oxidation Event, made it possible for more complex organisms, like animals and eventually humans, to evolve. But here's the twist. If life hadn't changed the atmosphere in that way, complex life might never have appeared. So life didn't just adapt to the planet, it actually built the conditions it needed to become more complex. That's the heart of the new theory. It suggests that given enough time and the right kinds of feedback between life and environment, complex life is bound to happen. In other words, we may not be a cosmic accident, we may be part of a cosmic pattern. One of the most powerful parts of this new model is its relationship with time. Carter's old theory emphasized that human evolution took almost the entire lifespan of the Earth, which made it seem like a long shot. But the Penn State researchers see this long timeline differently. They argue that the slow unfolding of complex life isn't proof of rarity, it's a sign of inevitability. Life takes time to build the necessary conditions for complexity, and once those conditions are in place, evolution can take the next steps. Think of it like planting a seed. Just because a tree takes a long time to grow doesn't mean it won't grow. It just means you have to be patient and give it the right environment. Under this view, planets that are similar to Earth and have life-supporting conditions for billions of years might naturally produce intelligent beings, just like Earth did. So the question becomes not, how lucky are we, but how many other planets have had enough time for this to happen? The new model also emphasizes the importance of feedback loops between life and its environment. A feedback loop is a process where the output of a system loops back to influence the system itself. On Earth, these loops are everywhere. Here are just a few examples. Carbon cycle. Plants absorb carbon dioxide, which cools the planet. Cooler temperatures make the planet more livable, which allows more plants to thrive, which in turn absorb even more carbon. Oxygen and evolution. Early life created oxygen, which allowed new life forms to evolve that needed oxygen. Climate and complexity. Life influences Earth's climate through greenhouse gases, and climate changes shape the paths of evolution. Over billions of years, these loops allow life and planet to work together, creating a stage where complexity can arise. It's like a long, slow dance between biology and geology, where each step makes the next one more likely. If this new model is correct, it has enormous implications for how we search for life beyond Earth. For decades, many scientists have assumed that intelligent life must be extremely rare. This belief has influenced how space agencies like NASA or ESA search for alien worlds. Most of their focus has been on finding simple life, bacteria-like organisms, because complex life was assumed to be too unlikely. But if complex life is actually a natural outcome of planetary evolution, then our search might need to change. Instead of looking for rare miracles, we could be looking for inevitable patterns. That means we might want to look for planets with signs of geological activity, which helps cycle nutrients, worlds with liquid water, which is essential for most forms of life we know, atmospheres with chemical imbalances, which could suggest biological processes, planets that are old enough to have gone through long-term environmental evolution. With this approach, our odds of finding alien life, maybe even intelligent life, suddenly don't seem so small. For a long time, humans have wondered whether we're special. Are we the only intelligent beings to ever exist? Or are we just one example among many? Carter's hard steps model gave us a kind of cold comfort. Yes, we are alone, but that makes us special, perhaps even chosen. But this new model offers a different kind of comfort. It suggests that we are not unique, but part of a much larger story written across the stars. If the emergence of intelligent life is a natural result of planetary evolution, then maybe civilizations like ours have happened many times before, and will happen again. That idea can be a little unsettling. It means we're not the center of the universe, but it's also beautiful. It means we're not isolated. We're connected to something far bigger than ourselves. This new theory doesn't have all the answers. There are still many mysteries about how life begins, how intelligence evolves, and whether we'll ever find evidence of other civilizations. But it changes the tone of the questions. It gives scientists new directions to explore and new reasons to be hopeful. Some of the biggest questions that researchers might now focus on include: what are the universal rules of planetary evolution? What specific environmental changes are needed to trigger complexity? Can we find these patterns on exoplanets, worlds orbiting other stars? What can Earth's own history teach us about other possible Earths? And most importantly, if we're not alone, where is everyone? The new model developed by the Penn State researchers offers a more optimistic, more vibrant view of the cosmos. Instead of imagining a silent universe where we are the only intelligent voice, we can now begin to imagine a universe humming with potential. Somewhere, orbiting a distant star, there may be a world like ours, a place where simple life has already begun the long journey toward complexity. Perhaps that world is still in its microbial stage, or maybe it has already evolved animals, ecosystems, even civilizations. We don't know yet. But we're beginning to learn how to look, and the more we learn, the more we realize that Earth may not be the only place where the universe has opened its eyes. When we look at the world around us today, full of people, animals, plants, insects, and countless other life forms, it might seem like life has always been here. But the truth is far more fascinating. Life, especially complex life like animals and humans, took billions of years to develop. In a new and thought-provoking study, a group of researchers made a bold claim. Earth wasn't always a place where life could thrive. In fact, in its early days, Earth was more like a harsh, dangerous world, not a friendly home for living things. These researchers, who were experts in both space science, astrophysicists, and life science, geobiologists, came together to understand how Earth changed over time. Their idea is simple, yet powerful. The early Earth was not ready for complex life, and it was only after many changes in the planet's environment that complex organisms were able to appear. This turning point, when Earth finally became a permissive place for life, is one of the most important events in our planet's history. Let's take a closer look at how Earth slowly transformed from a lifeless rock into a world bursting with life, and how everything from bacteria to human beings became possible only after certain environmental conditions were met. In the very beginning, around 4.5 billion years ago, Earth was nothing like it is today. It was hot, violent, and covered in molten lava. Volcanoes constantly erupted, and the air was filled with toxic gases like methane, carbon dioxide, and ammonia. There was no oxygen in the atmosphere, no blue skies, and certainly no oceans filled with fish or land crawling with animals. In this early stage, the environment was anything but friendly to life. Even the most basic forms of life, like simple single-celled organisms, would have struggled to survive. But somehow, tiny sparks of life did appear. Most scientists believe that the earliest life on Earth began more than 3.5 billion years ago in the form of simple microbes. These microbes lived in extreme conditions, like deep sea vents or hot springs. But even though these first life forms managed to survive, they were extremely simple. They didn't breathe oxygen, they didn't move, they didn't think, and they didn't change much for billions of years. So what was holding back life from becoming more complex? To understand how life became more complex, we need to understand oxygen, the gas we breathe every moment of our lives. Oxygen is not just important for humans and animals, it is the key ingredient that allows complex cells to exist. Without it, we wouldn't be here. But in the early days of Earth, there was almost no oxygen in the air. This changed thanks to some amazing tiny organisms called cyanobacteria, also known as blue-green algae. These tiny creatures had a superpower. They could do something called photosynthesis. Just like plants today, cyanobacteria could take sunlight, carbon dioxide and water and turn them into energy. But there was a side effect: oxygen. As these bacteria went about their lives, they quietly began releasing oxygen into the atmosphere. At first, this oxygen didn't stick around. It was absorbed by iron and other chemicals in the oceans and on land. But over time, the oxygen began to build up. Slowly, over hundreds of millions of years, the Earth's atmosphere changed. This great event is called the Great Oxidation Event, and it happened about 2.5 billion years ago. It was one of the biggest environmental changes in the history of the planet. Still, even after this event, oxygen levels were not high enough to support animals. It would take even more time, another 1.5 billion years, before oxygen reached the right levels to support complex life. The idea of Earth becoming permissive is central to the new study. Dan Mills, the lead author of the research and a postdoctoral scientist at the University of Munich, explains that certain steps in evolution simply could not happen until the environment was just right. In other words, Earth needed to unlock certain levels of oxygen and other conditions before animals could evolve. Think of it like this. If evolution is a race, the runners are ready to go, but the track isn't finished yet. Until the track is built and the conditions are safe, the race can't start. For millions, no billions of years, simple life was just waiting. Microbes ruled the world. Some formed mats on the seafloor, others floated in the oceans. These creatures were small and slow-growing, but they were slowly shaping the planet in ways that would eventually allow more complicated life to take over. The scientists in the study call this process environmental permissiveness. It means the planet's systems, its air, water, rocks, and chemistry, had to reach a specific balance to allow new forms of life to evolve. That balance did not happen overnight. It took countless changes in Earth's climate, oceans, and atmosphere. Let's imagine Earth during the long wait between the first oxygen-producing bacteria and the rise of animals. During this time, oxygen levels slowly crept upward, sometimes rising, sometimes falling. The oceans remained full of life, but it was still all microbial, tiny, invisible organisms. Then, about 800 million years ago, something began to change. There is strong evidence that oxygen levels began to rise more quickly during this time. No one knows exactly why, but it might have been due to tectonic shifts in the Earth's crust, changes in volcanic activity, or the burial of organic carbon in ocean sediments. These changes may have allowed more oxygen to stay in the atmosphere instead of being used up by chemical reactions. Around 600 million years ago, we see something incredible in the fossil record: the first signs of multicellular life. These were soft-bodied creatures, very different from animals today, but they were a clear step forward. And then, just a few million years later, almost like an explosion in the history of life, animals began to evolve rapidly. This event is known as the Cambrian explosion, and it happened around 541 million years ago. During this time, life exploded into diversity. Animals with shells, eyes, limbs, and nervous systems began to appear. Almost all the major animal groups we know today can trace their roots back to this period. But none of this would have been possible without the right environmental conditions, especially the right amount of oxygen. The study emphasizes that this wasn't a one-way street. Life didn't just wait for the environment to change, life also changed the environment. For example, those early microbes that produced oxygen helped transform the atmosphere, and later, the first plants helped stabilize Earth's climate and increase oxygen even more. This feedback loop, where life affects the environment and the environment affects life, is one of the most important ideas in science. While oxygen was a major piece of the puzzle, it wasn't the only one. Complex life also needed other conditions to be just right. For example, nutrient availability. Complex life needs more energy and more nutrients such as phosphorus and nitrogen. These nutrients had to become more available in the oceans. Stable climate. Extreme swings between hot and cold could wipe out life. Earth needed a more stable climate to support long-term evolution. Protection from radiation. Earth's magnetic field and ozone layer had to be strong enough to shield life from harmful radiation from the sun. All of these factors took time to fall into place. This new study asks us to look at evolution in a new way. Instead of thinking that life randomly got lucky, we can start to see evolution as a natural result of Earth's changing environment. As Dan Mills and the other scientists explain, once the right conditions were in place, the steps toward complex life became more likely. That means intelligent life, like humans, might not be as rare as we once thought. If other planets go through similar environmental changes, they too might eventually reach a permissive state, and when that happens, life could emerge there as well. In other words, we may not be alone. This new way of thinking has big implications, not just for how we understand Earth, but for how we look at other planets. For example, when scientists search for life on planets like Mars or moons like Europa or Enceladus, they are looking not just for signs of water, but for signs that the environment may have been permissive at some point. And when we look at distant exoplanets orbiting other stars, we can now ask, is this planet's environment moving in the right direction? Has it reached the right balance for life? The study helps expand our definition of what a habitable planet really means. Life on Earth is still evolving, and our planet is still changing. We are part of this long story, a story that began over 4 billion years ago, when the Earth was a fiery ball of molten rock. It took more than 2 billion years just to build up enough oxygen for simple animals. It took another 1 billion years before animals evolved complex body plans, nervous systems, and the beginnings of intelligence. Now humans are exploring the stars, asking questions about life beyond Earth, and trying to understand how we fit into the universe. This study reminds us of just how special Earth is, and how much patience it took for the planet to become what it is today. Life did not appear suddenly. It was not instant. It was a slow and beautiful unfolding guided by chemistry, chance, and the changing face of our world. We are living proof of what can happen when a planet finally becomes ready. For a long time, many scientists believed that intelligent life, like the kind humans represent, was the result of a very lucky series of events. According to this way of thinking, life had to overcome one impossibly difficult challenge after another to reach the level of intelligence we now see on Earth. These challenges were so hard, some said, that the odds of them happening again somewhere else in the universe were extremely small. But now, a new idea is starting to change the way we see things. One of the people helping to lead this new perspective is a researcher named Mills. As a young scientist, Mills spent time working in a research lab at Pennsylvania State University, also known as Penn State, under the guidance of an astrobiologist named Professor Jennifer McCalady. In the lab, Mills and other students explored deep questions about how life begins, how it evolves, and whether it might exist elsewhere in the universe. We're arguing that intelligent life may not require a series of lucky breaks to exist, Mills explained in a recent interview. In other words, he and his team believe that life doesn't have to win the cosmic lottery to become intelligent. Instead, they suggest that intelligent life might arise naturally, almost as if it were destined to happen under the right conditions. According to Mills, the human story is not about showing up either early or late in the history of our planet. It's more accurate to say that humanity arrived exactly on time. That is, our evolution happened when the environmental and planetary conditions were just right to support intelligent life. Perhaps it's only a matter of time, he said. And here's where things get even more exciting. Maybe other planets in the universe reach those life-friendly conditions faster than Earth did. Or maybe some are still on their way. The point is that Earth might not be the only place where intelligence can, or will arise. This idea challenges an older theory that has shaped scientific thinking for decades. That older theory is called the hard steps model, and it is based on a rather bleak prediction that intelligent civilizations like ours are incredibly rare in the universe, perhaps so rare that we might be the only ones that have ever existed. Let's take a closer look at both theories and see how this new way of thinking could completely change how we view life, intelligence, and our place in the cosmos. The hard steps model comes from the work of a British physicist named Brandon Carter. Carter was interested in understanding why humanity appeared relatively late in the life of our planet. Earth is estimated to be about 4.5 to 5 billion years old, and the Sun, the star that gives our planet light and warmth, is expected to last for about 10 billion years in total. If Earth is already about halfway through its life under the Sun, and intelligent life like humans only showed up in the last few million years, doesn't that suggest that becoming intelligent is really, really hard? That was Carter's big question. Carter proposed that the evolution of intelligent life depends on passing through a number of rare and difficult steps, each of which is unlikely to occur in any given time frame. According to this theory, these steps include the origin of life, going from non-living chemicals to the first tiny self-replicating organisms, the development of complex cells, not just single cells, but cells with internal structures like nuclei, which are the building blocks of more advanced life, multicellular life, organisms made of many cells working together, like plants and animals, consciousness and intelligence, the ability to think, feel, learn, and build civilizations. Each of these steps, Carter believed, might be so improbable that the chance of all of them happening on a single planet is astronomically low. If that's true, then Earth is an incredible exception, and the rest of the universe is likely silent, full of lifeless rocks and oceans that never managed to spark consciousness. This theory left many people feeling both special and isolated. On one hand, it suggested that we are truly unique. On the other hand, it also meant that we might be forever alone. But what if Carter's basic assumption, that intelligent life must arise late because the steps are so difficult, is wrong? Mills and his colleagues have a different explanation. They think that Earth's timeline for developing intelligent life wasn't particularly early or late. It was simply on time. That means human beings appeared exactly when the conditions allowed for it to happen. In this view, life doesn't need to beat impossible odds. It just needs time, stability, and the right environmental support to evolve. Let's imagine Earth as a kind of cooking pot. In the beginning, the pot was too cold. Life couldn't get started. Then, as the planet warmed up and stabilized, ingredients like water, sunlight, and simple molecules began to mix. After a while, something remarkable happened. Primitive life began. Then, over billions of years, that life became more and more complex, like a slow-simmering stew. The important point here is that none of the steps were necessarily improbable or miraculous. They just needed time, just as bread needs time to rise or a tree needs time to grow. The more time a planet has under the right conditions, the more likely it becomes that life will not only start but also evolve toward intelligence. This is what scientists call a permissive environment. It means an environment that allows something to happen rather than actively blocking it. In the early days of Earth, the environment was not very permissive. The air lacked oxygen. The oceans were filled with harmful chemicals. Temperatures rose and fell dramatically. All of these factors made it hard for life to thrive. But over billions of years, Earth changed. Volcanic activity created continents. Microbes filled the atmosphere with oxygen. The climate stabilized. And eventually, life found the room it needed to grow more complex. First came simple cells, then more advanced ones, then animals, then humans. It wasn't a miracle, it was a process. And if Earth went through this process, couldn't other planets do the same? This is where the new idea becomes truly exciting. If life just needs time and the right environment to evolve toward intelligence, then Earth might not be a 1 in a trillion miracle. Instead, it could be just one example among many. Imagine there are billions of planets orbiting stars across the Milky Way galaxy. Some of those planets formed before Earth, some formed after. Each one has its own unique history, with different climates, different chemical makeups, and different timelines. Some planets might have reached life-friendly conditions very quickly, perhaps in just a few 100 million years. In those worlds, intelligent life could have emerged billions of years ago. Who knows what kinds of beings might live there today if they survived and advanced? Other planets might still be in their early stages, too hot, too cold, or too unstable. But given enough time, they too might reach the point where complex life can flourish. It's even possible that Earth is somewhere in the middle of the cosmic timeline. Not early, not late, but average. That would mean intelligent life might be more common than we ever imagined. And here's a wild thought. Maybe some civilizations rose, flourished, and disappeared long before Earth ever existed. The hard steps theory gave us a universe that is mostly silent, mostly empty, and mostly lifeless. But this new way of thinking paints a different picture. It suggests a universe filled with planets that are slowly waking up just as Earth once did. Imagine a garden of seeds. If the soil is rich and the conditions are right, those seeds will eventually sprout. Some might bloom quickly, others may take years, but the point is, they will bloom, given time. In this analogy, Earth is just one seed that happened to bloom around 4.5 billion years after its formation. Other seeds might bloom earlier, some might bloom later, and some might never bloom at all. But the process itself is not a fluke, it's natural. This shift in thinking has major consequences for how we search for life in the universe. For decades, scientists have been trying to answer the question, are we alone? They've used telescopes to scan the skies for signs of alien radio signals. They've sent robotic spacecraft to explore planets and moons in our solar system. They've studied ancient rocks on Earth to understand how life got started here. If the hard steps theory were true, then most of those efforts might be in vain. But if Mills and his colleagues are right, if intelligent life is just a matter of timing, then our search suddenly becomes much more hopeful. We might find signs of simple life on the icy moons of Jupiter and Saturn, like Europa or Enceladus. We might detect the chemical fingerprints of alien biology in the atmospheres of planets orbiting distant stars. We might one day pick up a signal from a civilization that evolved billions of years ago on a planet far older than Earth. This is not science fiction. It is the logical extension of the idea that life is not rare, it's just patient. Let's stop and imagine for a moment what this really means. It means the night sky isn't just full of stars, it's full of stories. Each star may have planets, each planet may have its own journey. Some are barren and dead, but others, perhaps many others, are alive. Some may have intelligent beings who look nothing like us, think in ways we cannot understand, and have built technologies we can barely dream of. Perhaps they too wondered if they were alone. Perhaps they searched the skies and found us, or are searching still. This is not just a scientific idea. It is a powerful, almost spiritual shift in how we understand ourselves. It means we are part of something much larger. We are not the only story. We are one chapter in a vast, unfolding book. At the heart of this new idea is a beautiful truth. Nature is patient. It does not rush. It does not need miracles. It simply follows the laws of physics and chemistry, slowly, steadily, building the conditions for life. On Earth, that process took more than 4 billion years. But look at what it produced. Oceans, forests, cities, art, music, mathematics, love. Now imagine what might have happened in a world that had a head start. What could life become given 6 billion years, or 10? What civilizations might be waiting for us to discover them? And what might Earth become in the next billion years if we survive and grow? For a long time, people have tried to understand how and why humans appeared on Earth. Was it just luck, or was it something that was always going to happen? A new study, led by a group of scientists, offers a very interesting idea. These researchers say that the appearance of humans was not a random event or a miracle. Instead, it happened because of a natural chain of events that unfolded over billions of years. They believe the conditions that allowed humans to exist only came about recently, and they came about in a specific order that made life like ours possible. According to this study, the Earth did not start off as a planet where humans could live. In fact, for most of Earth's history, the planet was too harsh for creatures like us. The air didn't have enough oxygen, the oceans were too salty or too warm, and there weren't enough nutrients in the environment to support complex life. Over time, though, the planet changed. The air became more breathable, the temperature became more comfortable, and the oceans reached a level of saltiness that could support more life. These changes didn't happen all at once. They happened in stages, like doors slowly opening one by one. The scientists call these doors windows of habitability. Each window of habitability allowed new forms of life to emerge. At first, there were only tiny, simple life forms. Then, more complex organisms began to appear. Eventually, animals and plants came onto the scene. And finally, after all these stages were completed and the planet was ready, humans appeared. In other words, the Earth had to go through a long series of changes to become a place where human beings could survive and thrive. Jason Wright, a professor of astronomy and astrophysics at Penn State University, is one of the authors of the paper. He says that instead of thinking about life in terms of how long the sun will shine, we should think in terms of geological time. That is the time it takes for mountains to form, oceans to shift, and the air to change. He believes life evolves along with the planet itself, and so we must understand Earth's history to understand how life like ours came to be. These are normal timescales on the Earth, he explains. If life evolves with the planet, then it will evolve on a planetary timescale at a planetary pace. Let's explore what that means in simpler terms. Imagine Earth's history as a very long book. The first pages are mostly empty, with just a few simple lines. Those are the early forms of life, like single-celled organisms. As we turn the pages, the story becomes more detailed. Complex life begins to appear. The air starts to fill with oxygen, and plants and animals begin to take shape. Finally, near the end of the book, but not too late, humans arrive. It wasn't that we came early or late. We came exactly when the story had built up to the right moment. One of the biggest ideas in the study is that humans appeared not because of random chance, but because of how Earth changed over time. Things like temperature, ocean salt levels, nutrients, and oxygen all played a role. Each of these had to reach the right level before our kind of life could exist. For example, if the oceans had stayed too salty or the air had not gained enough oxygen, we might never have come into being. Let's look more closely at these factors. First, there's oxygen. For millions and millions of years, Earth's atmosphere had very little of it. But tiny life forms called cyanobacteria began to release oxygen into the air through photosynthesis, a process where they use sunlight to make energy. Over time, the amount of oxygen in the atmosphere grew. This change took a very long time, more than 2 billion years. Without this oxygen buildup, complex animals, including humans, could not have evolved. Our cells need oxygen to work, so it had to be there first. Next, let's talk about nutrients. Life needs food, not just in the sense of plants or animals eating, but also at the chemical level. Simple forms of life require certain chemicals like nitrogen, phosphorus, and iron. These nutrients had to become available in the right amounts and in the right places. For example, iron comes from the Earth's crust and reaches the oceans through weathering and erosion. If these nutrients weren't available in the oceans and soils, then early life forms couldn't grow or evolve into more complex ones. Again, this took millions of years. Then there's sea surface temperature. Water covers most of our planet, and most life started in the oceans. But the temperature of that water matters a lot. If it's too hot or too cold, life struggles. Early in Earth's history, the oceans were often much warmer than they are today. As the Earth cooled, the temperature of the oceans also dropped. Only when the water reached the right range, not too hot, not too cold, could complex life start to flourish. Also important is ocean salinity, or how salty the ocean water is. Salt levels in the ocean affect how cells function. If the water is too salty, cells can't keep their shape or function properly. If it's not salty enough, the balance of water and chemicals inside living things gets thrown off. Over billions of years, Earth's oceans changed, gradually reaching a level of salinity that could support complex forms of life. What this study is saying is that all these things, oxygen, nutrients, temperature, and salt, had to align. It wasn't enough for just one or two of them to be right. They all had to reach the correct levels at the same time. When that happened, Earth opened a window of habitability, a time when the planet could support more complex life, including human beings. And once that window opened, human evolution became possible. Think of it like baking a cake. You need the right ingredients: flour, sugar, eggs, butter, and they must be combined in the right amounts. Then you need the right temperature, and you need to wait the right amount of time. Only when all the steps are followed will the cake turn out right. Earth was like that too. For billions of years, it was gathering ingredients and changing conditions, until finally, all the elements were in place to bake intelligent life. The researchers believe that this process was not just something that happened on Earth. They think it could happen on other planets too. If a planet has the right mix of elements and goes through the same kinds of changes, it might eventually support intelligent life. But it would still take billions of years. That's why they suggest using geological time, not just the lifespan of stars, to think about how life appears. Life doesn't just pop up quickly. It needs time, a lot of time. This way of thinking is different from older ideas. Some scientists used to think that Earth was just incredibly lucky, that all the right things happened by chance, and that humans are a rare accident. Others thought that life could appear very quickly wherever conditions were right. But this new study says something in between. It says Earth's journey made the rise of humans likely, but only because the planet itself went through a long, slow transformation. To truly understand what this means, let's go back in time, way, way back. The Earth is about 4.5 billion years old. For the first few 100 million years, it was a dangerous place. Meteors crashed into it often. Volcanoes erupted constantly. There was no breathable air and no oceans, but slowly the planet cooled. Water vapor formed clouds and rain began to fall. Oceans formed. Simple life may have started in these oceans as early as 3.8 billion years ago. For the next 2 billion years, life remained simple, mostly single-celled creatures. Then, around 2.5 billion years ago, something amazing happened. Some microbes began to use sunlight to make food, releasing oxygen as a waste product. This was the beginning of what scientists call the Great Oxygenation event. Oxygen levels started to rise slowly at first, then more quickly. But it still took hundreds of millions of years before there was enough oxygen for larger animals to exist. Over the next billion years, nutrients began to spread more evenly through the oceans, and temperatures started to stabilize. Around 600 million years ago, animals with many cells, known as multicellular organisms, began to appear. By 500 million years ago, a wide variety of sea life had emerged, including the ancestors of fish, insects, and even early vertebrates. By about 360 million years ago, some creatures had begun to crawl onto land. Plants and animals started to fill forests, rivers, and coastlines. Mammals evolved around 200 million years ago. And finally, after a long line of evolutionary steps, early humans appeared about 200,000 years ago. To put that into perspective, the Earth's history is like a clock with 24 hours. If Earth formed at midnight, then humans only appeared in the last few seconds before the next midnight. That's how recent we are. But we appeared when everything was finally ready, when all the windows of habitability had opened. This idea changes how we think about life, both here and elsewhere. It suggests that if we want to look for intelligent life on other planets, we need to ask more than just whether the planet is warm or has water. We need to look at how old the planet is, what kind of atmosphere it has, and whether it has gone through the same long journey that Earth did. Only then can we begin to guess whether it might support intelligent beings like us. However, this study reminds us that life is not only a biological story, it's also a geological one. The rocks, the air, the oceans, they all shaped who we are, and perhaps most important of all, they shaped who we are. Humans did not come too early or too late. We came right on time, in step with Earth's own rhythm, as part of its long unfolding story. For many years, the dominant belief among scientists about the rise of intelligent life was a rather pessimistic one. The idea, known as the hard steps model, suggested that intelligent life like humans was extremely rare and required a very unlikely series of fortunate events. According to this view, life needed to win the cosmic lottery, not just once but many times over, before something as complex as a human being could finally emerge. In this model, intelligent beings were not a natural outcome of evolution, but rather a strange exception, the result of multiple hard evolutionary steps that had to happen in just the right order. But now, a group of scientists is challenging that long-standing belief. They are saying that maybe life, especially intelligent life, is not so improbable after all. Maybe it doesn't require winning a cosmic lottery. Maybe it simply requires time, the right conditions, and the natural unfolding of the planet's story. At the heart of this exciting shift in thinking is a powerful collaboration between two very different branches of science, astrophysics and geobiology. One focuses on stars, planets, and galaxies. The other looks at life on Earth, how it began, how it changed, and how it continues to adapt to the world around it. These two fields, which for so long seemed far apart, have now come together like two banks of a river finally connected by a strong and thoughtful bridge. To understand why this new perspective matters so much, it helps to look back at the older idea it's replacing. The hard steps model was originally developed by scientists who studied the stars and the vastness of space. One of those scientists is Jason Wright, an astrophysicist at Pennsylvania State University. He explained that the model gained popularity partly because it came from the world of astrophysics, a field that has long been the foundation for understanding planets and the formation of solar systems. In astrophysics, the focus is often on large numbers and long timelines. Scientists look at billions of years and countless stars to make sense of how the universe works. When astrophysicists considered the origins of intelligent life, they assumed that life had to go through a series of highly unlikely steps, such as the jump from simple single-celled organisms to more complex life forms, and then from animals to intelligent beings capable of thought and culture. These were seen as hard steps because they didn't seem guaranteed. If even one of them failed to happen, intelligent life would never appear. This belief shaped not only our understanding of life on Earth, but also our expectations about life elsewhere in the universe. If life required many rare and unlikely events, then the chances of finding intelligent beings on other planets seemed very small. Earth, in that view, was probably one of a kind, a lucky winner in a universe full of empty worlds. But Jason Wright and his colleagues began to question this old idea. What if those steps weren't as hard as we thought? What if intelligent life doesn't require a miracle but is in fact the result of natural processes that can unfold under the right conditions? To explore this idea, Wright joined forces with scientists from a very different field, geobiology. Geobiologists study the deep history of Earth's environment and the life it supports. They look at things like changes in the planet's temperature, the levels of oxygen in the atmosphere, and the nutrients available in the oceans. These environmental factors play a huge role in shaping how life evolves over time. Among the geobiologists involved in the study was Jennifer McCalady, who directs the Astrobiology Research Center at Pennsylvania State University. She said something beautiful and powerful about this collaboration. This paper is the most generous act of interdisciplinary work. What she meant was that it wasn't easy for two very different scientific worlds to come together. Astrophysicists and geobiologists speak different scientific languages. They focus on different questions and use different tools. But for this study, they decided to meet in the middle. McCalady continued, "Our fields were far apart, and we put them on the same page to get at this question of how we got here and are we alone. There was a gulf, and we built a bridge. And that's exactly what they did. They built a bridge of shared ideas, one that connected the stars above with the Earth below. This bridge allowed them to think in new ways about the conditions that made intelligent life possible, not just on Earth, but possibly elsewhere in the universe as well. Instead of seeing life as a string of random lucky breaks, this new study looks at life as a natural outcome of planetary evolution. The idea is simple but powerful. Planets like Earth go through stages. As they change, they create what the researchers call windows of habitability, periods of time when the environment becomes suitable for life to not just exist, but thrive and evolve. Imagine Earth's long history as a movie that has been playing for more than 4 billion years. In the beginning, the stage was dark and hostile, too hot, too barren, too unstable for life to gain a foothold. But over time, Earth's surface cooled, water gathered, atmospheres formed, and as the planet changed, so did the opportunities for life. In this new view, each major step in the evolution of life didn't happen because of luck. It happened because the environment became ready for it. For example, complex life like animals couldn't exist until there was enough oxygen in the atmosphere. That oxygen didn't appear by magic. It was the result of tiny microbes that had been busy for hundreds of millions of years, slowly pumping oxygen into the air through a process called photosynthesis. Eventually, the oxygen reached a tipping point. When that happened, the window opened. Complex life stepped through. In this way, Earth's history becomes a sequence of natural openings, moments when the conditions were just right for life to take the next leap forward. What makes this new model so exciting is that it treats Earth not as a rare miracle, but as a typical example of how life might evolve on planets across the universe. If other planets go through similar environmental changes, if they also have oceans, tectonic activity, atmospheric chemistry, and cycles of nutrients, then they might also produce life. And not just any life, intelligent life. This is a big change from the hard steps model, which made it seem like intelligence was almost impossible. In that old view, Earth was the lucky winner, and we shouldn't expect to find another planet with creatures who can think, dream, and wonder. But the new model says something different. It says that intelligent life might actually be the natural result of a planet maturing over billions of years. Given enough time and the right conditions, life might climb that ladder again, and again, and again, on countless worlds. That doesn't mean intelligent life is everywhere. It still takes billions of years for a planet to become ready. It still requires the right mix of ingredients. But it's no longer seen as impossible. It's no longer viewed as a miracle. It's viewed as inevitable. This revolutionary idea didn't come from just one field of science. It came from cooperation. It came from astrophysicists and geobiologists deciding to listen to each other, to learn from each other's work, and to ask big questions together. For example, astrophysicists bring an understanding of how stars and planets form, how solar systems evolve, and how common certain planetary features might be. They know what types of planets are likely to exist and where they might be found. Geobiologists, on the other hand, offer deep knowledge of what life needs to survive and grow. They understand how the planet's chemistry, temperature, and atmosphere affect life's chances. They study fossils, rocks, and ancient microbes to learn how life responded to Earth's changing conditions over billions of years. By combining these two viewpoints, the researchers could build a more complete picture. They could see not just the hardware, the planet, but the software, the biology. They could begin to understand how planets become living worlds, and how living worlds might give rise to minds. This shift in thinking doesn't just change how we view Earth, it changes how we look at the entire universe. In the past, many people believed that Earth was special, a one-of-a-kind planet in a cold and empty cosmos. But if intelligent life is the natural result of planetary evolution, then the universe might be filled with other Earths, at different stages of development. Some of these planets might still be young and lifeless. Others might be teeming with simple organisms. Still others might be on the edge of a breakthrough, just waiting for the next environmental window to open. And somewhere out there, perhaps in a distant corner of our own galaxy, there might be a planet where intelligent beings have already stepped through those windows. Beings who have asked the same questions we ask, who have built their own bridges between disciplines, who have wondered, like us, whether they are alone. This new way of thinking isn't just a scientific idea. It touches on some of the deepest questions we can ask. Where did we come from? Why are we here? Are we alone? By building bridges between different fields, scientists are getting closer to answers. They're showing us that life may not be a cosmic accident. It may be a cosmic pattern, one that unfolds naturally when the right pieces fall into place. And if that's true, then we live in a universe that is not just vast and mysterious, but also deeply connected. A universe where the rise of life, and even intelligence, may be part of the story. Not the exception, but the rule. As more scientists join this journey, more bridges will be built. Astrophysicists will continue to explore distant stars and search for exoplanets that might be like Earth. Geobiologists will keep digging into the past, learning more about the hidden history of life on our own planet. And together, they will keep asking the big questions. Not just how we got here, but what it means to be here, and what we might find if we look far enough, deep enough, and bravely enough into the dark and beautiful sky. A biosignature, also sometimes called a chemical fossil or molecular fossil, is any kind of material or pattern, such as a special atom, a type of molecule or a physical change in an environment that could act as a clue that life once existed or still exists on a planet. Scientists look for these signs because they might point to living things that are too far away or too tiny to see directly. These signs can come in many forms. They might include the shapes or structures built by living things, the energy they use, or the waste they leave behind. Even simple things like the presence of oxygen in a planet's atmosphere can act as hints. The scientific field that studies life in space, called astrobiology, relies heavily on these biosignatures to look for life beyond Earth. When scientists find possible biosignatures, they can use them to understand how life might have begun, not only on Earth, but also on other planets like Mars, Venus, or even on distant worlds far across the galaxy. But knowing whether a strange chemical or feature is really caused by life, or by something else entirely, is not easy. In fact, figuring out if something is truly a biosignature takes a lot of careful thinking and testing. Scientists use 3 main rules when they look at a potential biosignature. It must be reliable, meaning it must come from life, and not from some natural process that doesn't involve life. It must last long enough, meaning it must survive until we can detect it, even if millions or billions of years have passed. It must be detectable, meaning we must have the technology to find and measure it. Let's take a closer look at each of these ideas. Firstly, a possible biosignature must stand out clearly from other things that might create similar effects. For example, life can sometimes create gases or materials that look exactly like the ones created by volcanoes, lightning, or chemical reactions in rocks. Scientists must be very cautious, studying every possible non-living explanation before deciding that life is the cause. It's interesting that life on Earth may have started by copying natural chemical reactions. Some scientists believe that early molecules were able to speed up certain geochemical reactions, grabbing energy from them. One such early life process is called methanogenesis, where simple life forms produce methane as a waste product. This process doesn't need oxygen and may have existed very early in Earth's history. In cases like this, scientists might look for signs of imbalance in a planet's chemistry, meaning something is happening either too much or too little, compared to what natural processes alone would do. This chemical imbalance, also known as disequilibrium, could point toward life being involved. The second rule is all about time. A biosignature must last long enough so that a space telescope, a robot probe, or even a future astronaut can find it. When living things use energy to survive, they often create waste products. These wastes can build up and stay behind for a very long time, becoming important clues. Also, sometimes the bodies or parts of organisms get buried and turned into fossils. On Earth, we have discovered fossils that are more than 3.5 billion years old. These preserved remains of very early life give us real proof that life existed long ago. So, some of the best biosignatures might be leftovers, like ancient waste, chemical traces, or fossilized remains. But in order for them to help us today, they must remain intact, meaning they must not be destroyed or changed too much over time. Even if a biosignature is real and has lasted through time, we still have to be able to see it or measure it with the tools we have. This may sound simple, but it's actually a big challenge. There are many ways life might exist on a faraway planet, yet we might completely miss it just because our telescopes or instruments aren't strong enough or advanced enough. Some possible biosignatures might be too faint to detect or may hide beneath clouds or thick atmospheres. So even if life is out there, we might get a false negative, a situation where life is present, but we just can't detect the signs. On the other hand, there are also false positives, times when something looks like life, but it's not. A good example of this is oxygen. On Earth, oxygen is mainly produced by photosynthesis, which is a process used by plants and other life forms to turn sunlight into energy. Oxygen is then used by many organisms to breathe. Because of this, scientists see oxygen as a strong biosignature. Also, oxygen is easy to spot because it shows up clearly in a planet's light spectrum, meaning it absorbs and reflects light in ways we can measure using telescopes. This makes it a great target. But there's a catch. Oxygen can also be made without life. One way this can happen is through a process called photolysis, where sunlight breaks water molecules apart and leaves oxygen behind. This can happen if a planet has too little of certain gases or if it loses a lot of water over time. So if we find oxygen on another planet, it's not automatically proof of life. We have to dig deeper to rule out all non-living causes. Figuring out whether something is really a biosignature or just a natural trick is one of the hardest parts of this kind of science. It takes smart thinking, creative ideas, and sometimes even a bit of luck. Scientists call this problem a degeneracy, where two completely different things, life and non-life, can produce the same results. Untangling this mystery is one of the main goals in the search for life beyond Earth. There are also problems caused not by nature, but by us humans. For example, many of today's telescopes do not have the high resolution needed to see very faint or very small biosignatures. Resolution refers to how sharp or detailed the images and measurements are. If a telescope can't zoom in far enough or break light into tiny enough parts, it might miss important clues. Also, building space probes and telescopes is a huge team effort, involving many scientists from different areas. Each group wants to study something different. Some want to look for water, others for the weather, some for stars and some for life. This means that the instruments on a space probe are often a compromise. For example, if one group wants a tool that looks for gases, another group might want one that measures heat. There's only so much space and power available, so sometimes the best tools for detecting biosignatures are left out or made weaker. That's why the search for life is not only about science and technology, but also about planning and teamwork. Every choice we make about what to build and where to look shapes what we might find, or what we might miss. Looking for life beyond Earth is a thrilling challenge, but it's also a careful and slow science. Biosignatures are like mysterious footprints left behind, and scientists must be detectives to figure out what made them. A true biosignature must come from life, not just from rocks or chemistry, last long enough to be discovered, be visible with today's tools and technology. At the same time, a scientist must avoid being fooled by false positives where non-living processes make something that looks like life. They must also prepare for false negatives, where real life hides itself too well to be seen. Long before humans walked the Earth, tiny life forms, especially microbes, were already living in oceans, lakes, and soils. Though these microscopic creatures are too small to see with the naked eye, they left behind chemical traces in rocks and sediments that scientists can still study today. These chemical traces, called biosignatures, act like invisible fingerprints of life. They help researchers understand where and when life existed, even billions of years ago. Over Earth's long history, which stretches back more than 4 billion years, some of these biosignatures have been preserved deep in ancient layers of rock. Studying these ancient records allows scientists to investigate how life interacted with the environment over time. It also helps us figure out what signs of life we should look for on other planets, like Mars. Experts in fields such as geochemistry, geobiology, and geomicrobiology are especially interested in these traces of life. They study the chemical elements, minerals, and tiny fossils found in rocks and sediments. Their goal is to figure out whether a certain sample once held living organisms, or still does. What exactly are biosignatures? Biosignatures can take many forms. Some of the most important examples include microfossils and stromatolites. These are tiny fossilized remains of ancient microbes or layered structures built by microbial communities. Biomarkers and isotopes, special molecules that only living organisms can make, such as certain kinds of fats or oils, and versions of carbon, nitrogen, and hydrogen atoms that are more common in living things. Isotopic ratios of sulfur and oxygen. The amounts of different forms of sulfur or oxygen atoms in a mineral can tell us if life helped create it. Redox-sensitive metals. Elements like iron, molybdenum, chromium, and rare earth metals can behave differently in environments where life is present. These markers are not just chemical curiosities, they are clues in a grand mystery. When found together in the right combinations, they strongly suggest the past or present existence of life. One fascinating example is how scientists use fatty acids to figure out what kinds of microbes live in a certain place. Fatty acids are key parts of the cell membranes in bacteria and archaea, ancient microbes that often live in extreme environments. Some fatty acids are so unique that they can even tell us the exact types of microbes in a sample. In another case, long-chain fatty alcohols with more than 23 carbon atoms are created by planktonic bacteria that drift in ocean water. These compounds can remain preserved in sediment layers for millions of years. In these situations, scientists often prefer the term biomarker instead of biosignature, because it specifically refers to molecules made by life. Another group of biomarkers includes straight-chain lipids like alkanes, alcohols and fatty acids with between 20 and 36 carbon atoms. These substances often come from the waxy outer coatings of plants, known as epicuticular wax, and are especially common in soils and peat, a kind of wetland material formed from decayed plants. Microbes don't just leave behind chemicals, they also change the structure of rocks. For instance, bacterial colonies can create tiny pores, just a few micrometers in size, inside carbonate rocks. When you look at these rocks under a microscope, these pores might look like regular mineral bubbles, but their shapes, sizes and patterns, such as swirling or branching forms, are unique. These features often hint at microbial activity. Still, not every odd shape or chemical in a rock is proof of life. Some non-living or abiotic processes can create features that look very similar to biosignatures. That's why scientists are very careful and use many kinds of evidence before claiming that life was involved. The morphology, or shape, of something in a rock, like a fossil or a crystal, might seem to indicate life, but this is one of the trickiest clues to interpret. For example, stromatolites, which are dome-like layers of minerals made by microbial mats, are some of the oldest possible signs of life on Earth. However, similar shapes can also be formed by natural geological forces such as tectonic activity. A good example of this challenge is a rock found in West Greenland that appears to be about 3,700,000,000 years old. Some scientists thought it was a stromatolite made by ancient microbes, but others suggested that the structure was simply created by pressure and movement within the Earth's crust. A more famous case involves a meteorite from Mars known as ALH 84001. It contains tiny magnetite crystals and odd-shaped microscopic structures that some researchers believed looked like fossilized bacteria. At first, these were thought to be possible biosignatures, but most scientists later agreed that these shapes were far too small to be actual fossil cells. These debates taught scientists an important lesson. Morphology alone is not enough. Just seeing something that looks like life doesn't prove anything unless there's strong supporting evidence, like chemical or isotopic data. Today, the scientific community agrees that we need multiple lines of evidence to confidently claim that life once existed somewhere. No single molecule can prove that life once existed. Instead, scientists look for distinctive patterns in organic molecules, patterns that don't happen randomly. For example, molecules left behind by broken down cell membranes usually show a limited range of sizes, even numbers of carbon atoms, concentrated presence in certain layers. Another good example is amino acids. Life on Earth uses only left-handed amino acids, while non-living chemistry usually produces a mix of left and right-handed forms. Finding only left-handed amino acids would be a strong biosignature. And it's not just chemistry. Life can leave behind magnetic traces too. Certain microbes form magnetite crystals that align with Earth's magnetic field, a magnetic signature that non-living processes don't usually create. Some of the most useful biosignatures come from fossil fuels like crude oil and bitumen. These sticky, black substances formed from ancient life over hundreds of millions of years. They contain biomarkers, complex carbon-based molecules originally made by plants, algae, or microbes. These biomarkers are made of atoms like carbon, hydrogen, oxygen, nitrogen, and sulfur. Over time, the molecules become simpler as the living matter turns into oil. Still, many of the original patterns remain. Biomarkers help determine how old the oil is, what temperature and pressure it experienced, and where it came from. Because each oil deposit has its own unique set of biomarkers, like a fingerprint, scientists can trace how oil moved underground from its source rock to where it's found today. To analyze these delicate molecules, researchers use very sensitive equipment such as gas chromatography and mass spectrometry. These tools separate the different chemicals in a sample and measure their amounts with extreme precision. Even when biomarkers are present in very tiny amounts, these methods can detect them. Biomarkers are incredibly resistant to damage. They don't break down easily, even after long exposure to air, water, or heat. That makes them great for detecting oil spills, identifying the source of pollution, or even checking for contamination in lubricant oils. But scientists must also be cautious. If the rock samples have been exposed to contamination or microbial breakdown, the biomarker results could be misleading. That's why untreated rock samples may not always give trustworthy data. Biosignatures are nature's clues, chemical footprints left behind by life, sometimes billions of years ago. By studying them, scientists can explore the deep history of life on Earth and perhaps one day even prove that life exists or once existed beyond our planet. But these clues are subtle. They require careful study and many kinds of evidence to interpret correctly. Whether we are searching for ancient microbes in Greenland, hidden bacteria in Martian meteorites, or biomarkers buried deep within oil deposits, the challenge remains the same: to separate the whispers of life from the noise of geology. And if we listen closely and study wisely, the rocks may yet tell us stories of worlds teeming with life, on Earth and far, far beyond. The origin of life on Earth is one of the most fascinating and enduring mysteries in all of science. The process by which life began from non-living substances is called abiogenesis, a word that simply means life beginning from non-life. According to current scientific thinking, life did not just suddenly appear in a flash. Instead, it emerged gradually, step by step, through a long and complex journey of chemical and physical changes. Scientists believe that this transformation, from a lifeless Earth to a living one, was not a single moment or a single event. Rather, it was a long process that unfolded over millions of years. It began with the formation of a planet that could support life, a world with liquid water, a mild climate, and the right chemical ingredients. Over time, basic organic molecules started to form. These were the building blocks of life: simple carbon-based chemicals like sugars, fats, amino acids, and nucleic acids. Eventually, some of these molecules developed the remarkable ability to copy themselves, a crucial step in becoming truly alive. Others began to organize into tiny structures, like bubbles or membranes, that could separate the inside from the outside. Some even helped trigger the very reactions that created them, a process called autocatalysis. Slowly, out of this bubbling chemical soup came the first simple cells. Even though we have never directly seen life emerge from non-life in a laboratory, scientists have created many ideas and experiments to help us understand how it could have happened. The study of abiogenesis is all about figuring out how chemical reactions in Earth's early days may have slowly built up into something we would recognize as life. This area of research pulls together ideas from many scientific fields, especially chemistry and biology, but also geology, physics, and even astronomy. Modern life is built on the chemistry of two key elements: carbon and water. 4 important types of molecules play essential roles in keeping living organisms alive. Lipids, these are fats and oils, which form the membranes around cells. Carbohydrates, sugars and starches that provide energy and structure. Amino acids, the parts that make up proteins, which do the work inside cells. Nucleic acids, DNA and RNA, which store genetic information and pass it on to the next generation. For any theory of how life began to be convincing, it must explain where these molecules came from and how they started working together. One of the biggest questions in abiogenesis is this: how did the first molecules that could copy themselves come into existence? Many scientists believe that life may have begun in a time they call the RNA world. RNA is a molecule that, unlike DNA, can both store information and help chemical reactions happen, much like enzymes do. So it might have been the perfect starter molecule for early life. Later on, DNA took over the job of storing genetic information, and proteins became the main workers of the cell. But RNA may have come first. Some scientists take a different approach, known as the metabolism first idea. This theory says that before life could replicate, it needed a source of energy and a set of chemical reactions that kept going. These reactions might have started in special environments, like hydrothermal vents on the ocean floor, where heat and minerals constantly churned out energy and chemicals. One famous experiment helped open the door to understanding how life's building blocks could form from non-living materials. In the year 1952, two scientists named Stanley Miller and Harold Urey created an experiment that mimicked the conditions of the early Earth. They combined water, gases like methane and ammonia, and sparks of electricity to simulate lightning. Amazingly, after just a few days, they found that amino acids, the same ones used to build proteins in our bodies, had formed. Since then, researchers have found amino acids not only on Earth but also in space, inside meteorites, comets, asteroids, and even in the clouds of gas and dust where new stars are born. This suggests that the ingredients for life might be quite common in the universe. At some point, all the complicated chemistry and self-copying molecules led to the first true living cells. Scientists call the earliest known ancestor of all life LUCA, which stands for Last Universal Common Ancestor. LUCA was not the very first living thing, but it was the last one from which all modern life has descended. Researchers believe LUCA lived more than 4 billion years ago. Even though it was just a single-celled organism, LUCA was already very advanced. Its DNA contained at least 355 genes, and it made use of about 60 different proteins, many of which are still found in all life today. These genes and proteins helped LUCA produce energy in the absence of oxygen in an anaerobic environment, using a set of chemical reactions called the Wood-Ljungdahl pathway. LUCA also had the tools needed to read the genetic code and build proteins, such as ribosomes, messenger RNA, and transfer RNA. It could also make copies of its own DNA, thanks to an enzyme called DNA polymerase. But here's the problem: LUCA's machinery is incredibly complex. DNA polymerase is needed to copy DNA, but it is made using instructions found in the DNA. So how could the first such system ever get started? It seems like a chicken and egg problem. Many scientists believe the solution is that life began even more simply, without DNA or proteins. In the RNA world, RNA could both store information and help copy itself, so no DNA or complex enzymes were needed at first. There are different ideas about where life might have first formed. Some researchers think it began deep beneath the ocean, near white smoker hydrothermal vents. These are places where hot, mineral-rich water pours out of the seafloor, creating natural chemical gradients, kind of like batteries that could power early life. Others believe life could have started inside the rocks of Earth's crust, or even in shallow pools of water on the surface. What we do know is that Earth is the only planet where life has ever been found. But scientists are always looking for clues elsewhere. The Earth itself is about 4,540,000,000 years old. The earliest solid evidence of life, tiny fossilized microorganisms, comes from rocks that are at least 3,800,000,000 years old, found in Western Australia. Even older fossils dated between 3,770,000,000 and 4,280,000,000 years old were found in Quebec, Canada. These fossils may have formed soon after the oceans appeared, around 4,400,000,000 years ago during a time known as the Hadean Eon. Life, as we understand it, is something that can reproduce and evolve. That means it can make copies of itself, and those copies can have small differences or mutations that can lead to changes over time. This idea is central to Darwinian evolution. NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. Even the simplest living cell, like LUCA, needs many different molecules and systems working together to survive and reproduce, and all of these parts must be present at the same time for the system to work. That's why figuring out how it all started is such a difficult puzzle. Although Earth is still the only place where we know life exists, scientists are now searching the universe for other places that might support life. This exciting field of research is called astrobiology. In the year 2015, NASA laid out a bold plan to study how life might begin on other planets. Their goal was to find out how simple molecules, like nucleobases, amino acids, and sugars, could come together to form large self-replicating structures like RNA. These large molecules, known as informational polymers, may have been a crucial step in the path toward life. For many centuries, people believed that life could appear all by itself from non-living materials. This idea, known as spontaneous generation, was widely accepted from the time of the ancient Greek philosopher Aristotle all the way into the 19th century. According to this belief, simple animals, like worms, flies, and insects, could be born directly from rotting meat, mud, or other decaying organic matter. Many thought that life simply appeared by chance, without needing parents or seeds. But starting in the 17th century, some scientists and thinkers began to question this view. One early critic was the English physician and writer Thomas Brown, who challenged popular superstitions in his book Pseudodoxia Epidemica. In the year 1665, the English scientist Robert Hooke published drawings of tiny living things, the very first images of microorganisms ever seen. Just over 10 years later, in the year 1676, the Dutch scientist Antony van Leeuwenhoek used his handmade microscopes to discover even more tiny creatures, what we now call bacteria and protozoa. These were invisible to the naked eye and lived in water, soil, and even inside people. Van Leeuwenhoek did not believe in spontaneous generation. By the early 1680s, through many careful experiments, he came to the conclusion that living things could not just appear out of nowhere. He studied how meat spoiled when kept in sealed and unsealed containers, and he closely observed how insects laid eggs and developed. His results clearly showed that life always came from existing life. Another major blow to the idea of spontaneous generation came in 1668, when Italian scientist Francesco Redi showed that maggots only appeared in meat if flies could reach it to lay their eggs. When he covered the meat so flies couldn't touch it, no maggots formed. This was solid proof that life did not arise spontaneously. By the middle of the 19th century, most scientists agreed that spontaneous generation had been disproved. Long before these experiments, another idea had already taken shape. As far back as the 5th century before the birth of Christ, the philosopher Anaxagoras had suggested a radical theory called panspermia. This idea claimed that life might not have started on Earth at all, but came from somewhere else in the universe. In modern times, the panspermia theory proposes that life, or at least the building blocks of life, may have travelled to Earth on meteoroids, asteroids, comets, or even tiny planet-like objects called planetoids. This idea shifts the origin of life to another planet or moon, and suggests that life could be spread across the galaxy like seeds in the wind. One popular version of this idea speculates that life might have started on the planet Mars and later made its way to Earth. By the 19th century, new ideas about life's origins began to take shape. Between the years 1864 and 1867, English philosopher Herbert Spencer proposed that life could have slowly developed from simple non-living chemicals. In 1879, botanist William Turner Thistleton Dyer also explored these ideas in his writing on evolution and spontaneous generation. On the first day of February in the year 1871, the famous naturalist Charles Darwin wrote a letter to his friend, botanist Joseph Hooker. In it, Darwin shared a personal thought. Maybe life first began in a warm little pond filled with various chemicals like ammonia and phosphate, with sunlight, heat, and possibly lightning providing the energy to spark life. He imagined that under those conditions, a protein molecule could have formed. But Darwin also pointed out that if such a chemical mixture appeared in modern times, it would be quickly consumed by existing life forms, something that wouldn't have happened before life existed. In the early 20th century, two scientists, Alexander Oparin from Russia and J.B.S. Haldane from England, developed a more detailed version of this idea. In the year 1924, Oparin suggested that the earliest life forms might have slowly assembled themselves from a primordial soup, a thick mixture of organic compounds in Earth's early oceans. Haldane, writing in the year 1929, agreed and imagined these oceans as a hot, dilute soup full of the raw materials needed to build life. Another scientist, J.D. Bernal, later showed that these processes could have created many of the complex molecules life needs, like proteins and nucleic acids. In the year 1967, Bernal described three important steps. First, the creation of simple organic molecules called monomers. Second, the linking of these monomers into larger chains called polymers. And third, the transformation of these polymers into living cells. One of the most famous experiments in this field was carried out in the year 1952 by two scientists, Stanley Miller and Harold Urey. They wanted to see if organic molecules, like amino acids, could form naturally from simple gases under conditions similar to early Earth. They used a mixture of methane, ammonia, hydrogen, and water vapor, all inside a sealed container, and added sparks of electricity to mimic lightning. The result? Several kinds of amino acids formed, showing that life's building blocks could indeed arise from non-living materials. Bernal praised the experiment, but also reminded others that creating these molecules wasn't enough. We also need to understand how energy from the environment helped organize and maintain them. Later studies showed that early Earth's atmosphere might not have been so chemically friendly. Instead of being strongly reducing, lacking oxygen, it was likely weakly reducing or even neutral, making it harder to produce amino acids in large amounts. But when scientists added minerals like iron and carbonates, common in Earth's early oceans, the variety of amino acids increased again. Scientists also explored two other potential environments: the depths of the sea near hydrothermal vents and the vast reaches of outer space. Let's now go far back, almost 14 billion years ago, to just after the Big Bang. At first, only the lightest elements existed: hydrogen, helium, and lithium. These atoms started clumping together into clouds, which later collapsed to form stars. The earliest stars were huge and short-lived. Inside their fiery cores, heavier elements like carbon and oxygen were created. When these stars exploded as supernovae, they scattered these elements across the universe. Carbon, now the fourth most common element in space, was formed in the hearts of stars and released during their deaths. These elements were essential for forming rocky planets like Earth. Around 4,600,000,000 years ago, according to the nebula hypothesis, our solar system began to take shape. A cloud of gas and dust collapsed under its own gravity. Most of the material formed the Sun, while the rest flattened into a disk where the planets formed. Radiometric dating tells us that Earth is about 4,540,000,000 years old. The oldest solid bits of the solar system found in special meteorites support this number. During its early phase, called the Hadean Eon, from Earth's formation to around 4,031,000,000 years ago, the planet was not friendly to life. Earth was hot, constantly bombarded by asteroids, and had little atmosphere. Not long after its formation, around 4,480,000,000 years ago, it likely collided with a Mars-sized object named Theia. The debris from that collision formed our Moon. This impact also stripped away much of Earth's early atmosphere, leaving behind gases like water vapor, nitrogen, and carbon dioxide. The Earth's oceans likely began forming soon after the moon-forming event. This is supported by ancient crystals called zircons, found in Western Australia, that are about 4,404,000,000 years old. They contain oxygen signatures that suggest the presence of water. The early atmosphere acted like a giant chemical laboratory. Though Earth may have experienced intense volcanic activity, it might still have been mostly covered in water between 4,400,000,000 and 4,300,000,000 years ago. At this time, Earth had little solid crust, a wild atmosphere, and was bombarded by solar radiation, cosmic rays, and frequent asteroid strikes. One major event in early Earth history is called the Late Heavy Bombardment. It is believed to have occurred between 4,100,000,000 and 3,800,000,000 years ago. Scientists once thought this was a single cataclysmic event, around 3,900,000,000 years ago, that could have sterilized the planet, boiling away the oceans and blocking sunlight. However, more recent studies suggest this period was not one giant impact, but rather many smaller impacts spread out over time. Samples collected by Apollo astronauts from the Moon may have created a false impression that one big event occurred, since most were taken near a large impact crater called the Imbrium Basin. Evidence from Earth's rocks shows that multiple waves of impacts likely took place, both before and after the 3,900,000,000 year mark. These impacts may not have been strong enough to wipe out life entirely or prevent it from starting. If life did begin in Earth's oceans deep below the surface, more than 10 meters down, it would have been protected from damaging ultraviolet light and most of the impacts from space. Deep-sea hydrothermal vents, which are hot openings on the ocean floor, could have produced large amounts of organic compounds, perhaps even more than the Miller-Urey experiment suggested. The hottest and most energy-rich spots around 100 to 150 degrees Celsius, are home today to some of the toughest microbes on Earth: hyperthermophilic bacteria and thermoacidophilic archaea. These extreme environments may have been where life began, hidden deep in the darkness, nourished by the heat of the Earth. Scientists believe that life most likely began on Earth sometime between 3,480 million years ago and 4,320 million years ago. This huge stretch of time reaches far back into Earth's early history, when our planet was still very young and the environment was much harsher than it is today. The oldest minimum age for life on Earth comes from physical clues preserved in rocks. In the year 2017, scientists announced a remarkable discovery. They had found what could be the oldest physical evidence of life in a remote area of northern Quebec, in Canada, known as the Nuvvuagittuq Greenstone Belt. These clues were found inside layered rocks called banded iron formations, and they might be as old as 3,770 million years, or possibly even up to 4,320 million years. Inside these ancient rocks were structures known as microbialites, which may have been created by microorganisms, tiny living things, around the time when Earth's oceans were just beginning to form, roughly 4,400 million years ago, during a time period scientists call the Hadean. These microscopic creatures may have lived in or near hydrothermal vents, which are hot, mineral-rich cracks on the ocean floor. Interestingly, modern bacteria that live in these deep-sea vents today look very similar to those ancient ones. This has led many scientists to believe that life may have first started in such environments: hot, dark, and rich in chemicals rather than light. However, not all scientists agree with this interpretation. Some later research suggested that the features found in those rocks might not have been created by living organisms at all. Instead, they might have been formed by purely chemical reactions in water rich in silica, by strange chemical formations called chemical gardens, or by natural activity such as volcanic eruptions or circulating hydrothermal fluids. So, the debate continues. Elsewhere on Earth, other strong hints of ancient life have been found. For example, in southwestern Greenland, in rocks that are 3,700 million years old, scientists have discovered biogenic graphite, a special form of carbon that is usually associated with living things. Similarly, in Western Australia, in the Pilbara region, fossils of ancient microbial mats were found in chert rocks dating back 3,490 million years. Microbial mats are layers of microorganisms, similar to the ones that still form in shallow water today. More evidence comes from Akelia Island, near Greenland's Isua supracrustal belt, where rocks of the same age, 3,700 million years old, contain carbon isotopes that strongly suggest they were created by life. In nearby areas of the Isua belt, tiny pockets of graphite trapped inside crystals of a mineral called garnet were found alongside other elements vital to life: oxygen, nitrogen, and possibly phosphorus in the form of phosphate. These discoveries make the case for early life even stronger. In the same Pilbara region of Australia, another exciting clue was found. In perite-rich sandstone on what used to be an ancient beach, scientists uncovered tubular fossilized cells. These cells appear to have used photosynthesis, the process of turning light into energy, but in a strange way. They did it without oxygen, by oxidizing sulfur, much like some modern bacteria do today. Even older signs of life might come from graphite trapped inside ancient minerals known as zircons from a place called Jack Hills, also in Australia. These zircons are as old as 4,100 million years, suggesting that life might have already existed just a few hundred million years after Earth formed. Also in Pilbara, scientists found stromatolites, layered structures that are typically formed by photosynthetic microbes like cyanobacteria. These stromatolites are embedded in rocks from the Dresser Formation, which are about 3,480 million years old. These rocks show evidence of hot springs and shallow seas. The texture and shape of the stromatolites make it likely they were formed by living things. A different line of evidence comes from genetic studies using a technique called molecular clock analysis. This method looks at changes in DNA over time and suggests that the last universal common ancestor, Lusa, the great-great-grandparent of all life on Earth, may have existed even earlier, possibly before 3,900,000,000 years ago. Life needs the right chemicals to exist, and those chemicals came from the stars. Every chemical element, except for hydrogen, some helium, and a little bit of lithium, was made inside stars through a process called stellar nucleosynthesis. The basic building blocks of life, simple molecules like carbon-hydrogen, positively charged carbon-hydrogen, and positively charged carbon, can be formed when ultraviolet light from stars breaks up and rearranges atoms. These basic organic molecules are not just made on planets, they also form naturally in space. So where did Earth's first organic molecules come from? Scientists think there are two main possibilities. They formed right here on Earth, possibly created by powerful events like meteorite impacts, lightning, or the sun's radiation triggering chemical reactions. They arrived from outer space, a theory known as pseudopanspermia. In this idea, molecules formed in space clouds and rained down onto Earth aboard dust particles, comets, or meteorites. Organic compounds are molecules that contain carbon, and carbon is one of the most important ingredients for life. It is found everywhere, from the sun and stars to comets and planetary atmospheres throughout the solar system. In space, organic molecules form inside large clouds of gas and dust, or around dying stars, where radiation powers complex chemical reactions. Even molecules critical to life's genetic code, like guanine, adenine, cytosine, uracil, and thymine, have been discovered inside meteorites. These are the building blocks of DNA and RNA, which carry the instructions for life. The amino acid glycine, one of the simplest parts of proteins, has also been found in space dust and in material collected from the comet Wild 2. Comets are covered in dark, tar-like substances that form when simple carbon compounds are exposed to radiation. When these comets crash into Earth, they could have delivered massive amounts of organic materials. In fact, during a violent period in Earth's history called the Late Heavy Bombardment, it is estimated that up to 5 million tons of organic molecules may have fallen onto the Earth each year. Even today, about 40,000 tons of cosmic dust lands on our planet annually. One special group of organic molecules called polycyclic aromatic hydrocarbons, PAHs, are the most common complex molecules seen across the universe. They are made of carbon and are believed to have formed soon after the Big Bang. These molecules are found in nebulae, comets, meteorites, and even around newly forming stars and planets. They probably made their way into Earth's early oceans and may have played a key role in the chemistry that led to life. One star, named HH46IR, looks a lot like our Sun when it was very young. Around it is a disk of gas and dust filled with molecules such as cyanides, hydrocarbons, and carbon monoxide, many of the same ingredients that life uses. Pairs can be changed in space by reactions with hydrogen, oxygen, and hydroxyl groups to form even more complex compounds. These are the kinds of molecules living cells use to build themselves. Tiny dust grains from space can help create these molecules, acting like miniature laboratories. For example, the Murchison meteorite carried a molecule called uracil, part of RNA, and another called xanthine. Studies of their carbon isotopes show they were probably made far from Earth, in outer space. NASA scientists have even found signs that all 4 DNA bases, adenine, guanine, cytosine, and thymine, can be made in space. These discoveries suggest that the building blocks of life might not be unique to Earth at all. Sugar molecules like glycolaldehyde, which is an important part of RNA, have been found around young stars and inside meteorites. This shows that even the sweet chemistry of life was happening long before Earth had oceans or living cells. Back in the 1860s, scientists started doing experiments that showed something amazing. Simple carbon-containing ingredients, when mixed with certain common substances found in nature, called inorganic catalysts, could form molecules that are important for life. These were the basic building blocks that living things are made of. This discovery was a huge clue that life might have started from non-living materials through natural chemical reactions. But forming more complex molecules, like long chains of amino acids or sugars, known as polymers, is not so easy. Especially when we imagine this happening in the primordial soup, a name scientists use for the warm, wet mix of chemicals thought to exist on early Earth. In experiments like the famous Miller-Urey experiment in the 1950s and work by Jonah Rowe, scientists found that while many useful molecules formed, Many other molecules also appeared that could stop or disrupt the process of making larger, useful molecules. This made things more complicated. Interestingly, biology uses a very small group of just 20 amino acids to build all of its proteins, even though many more are possible in nature. Since life usually takes advantage of whatever is available, this raises a question. Why did life pick such a small group and ignore the rest? One possible answer involves a chemical called formamide. It's a simple molecule made from carbon, hydrogen, oxygen, and nitrogen. Formamide might have been very important because it can help make amino acids when combined with other simple chemicals like aldehydes and nitriles. It also might help make the building blocks of DNA and RNA. In the year 1861, a chemist named Alexander Butleroff discovered a process called the Formose reaction. He found that if you heat a simple chemical called formaldehyde with some metal ions like calcium, under the right conditions it can turn into various sugars like tetraces, pentaces, and hexaces. These are all types of sugar molecules that are important for life. Later, in 1959, a scientist named Robert Breslow suggested that this reaction might be autocatalytic, meaning that once it starts, it can help speed itself up. Some of the key components of DNA and RNA, like guanine and adenine, can be made from very simple gases like hydrogen cyanide and ammonia. Formamide, the chemical mentioned earlier, can actually produce all 4 of the RNA bases when it's gently heated in the presence of common earth minerals. This is exciting because formamide is found almost everywhere. It can form naturally when hydrogen cyanide reacts with water and becomes concentrated when water evaporates. Hydrogen cyanide is deadly to oxygen-breathing organisms, but on early Earth those didn't exist yet. So it could have freely participated in many important chemical reactions, including the creation of glycine, one of the simplest amino acids. Surprisingly, the essential parts of DNA and RNA can also form in outer space. For example, uracil, cytosine, and thymine can be made from a substance called pyrimidine, which has been found in meteorites. Scientists think pyrimidine may have been created in the hearts of dying stars known as red giants, or inside enormous clouds of gas and dust drifting between stars. All 4 RNA bases might also form from formamide during events that release a lot of energy, like meteor impacts on the early Earth. In laboratories that mimic early Earth conditions, scientists have managed to produce ribonucleotides, the basic units of RNA, using these reactions. Other experiments show that extremely cold temperatures can help form the DNA bases adenine and guanine by concentrating their chemical building blocks like hydrogen cyanide. But for cytosine and uracil, hot conditions like boiling may be necessary. In one remarkable experiment, scientists left a mix of ammonia and cyanide in a freezer for 25 years. When they checked it later, they found 7 amino acids and 11 different nucleobases had formed in the ice. Another study showed that a solution of urea exposed to freeze-thaw cycles and electrical sparks in a low-oxygen atmosphere produced many useful molecules like striazines, cytosine, uracil, and adenine. The freezing caused impurities to cluster in tiny pockets of water trapped in the ice, a phenomenon called eutectic freezing, which helped the reactions happen faster than expected. Proteins are made from chains of amino acids. On early Earth, there could have been several ways for these chains, called peptides, to form. Some methods involve very hot, concentrated environments where the joining of molecules happens more easily. Others rely on condensing agents, chemicals that help bring small molecules together. Researchers have found that cycles of wetting and drying, along with the presence of certain salts, can greatly improve the chance of amino acids like glycine sticking together to form chains. Mineral surfaces, such as pyrite, calcite, and rutile, can also help amino acids bond, but they might also break them apart. So while minerals are helpful, they probably weren't enough on their own to make long, useful protein chains. Something extra was likely needed to keep the process going. Scientists have identified many chemicals that might have acted as natural condensing agents on early Earth, including cyanamide, urea, carbon monoxide, carbonyl sulfide, carbon disulfide, sulfur dioxide, and diammonium phosphate, among others. A 2024 experiment used a piece of sapphire with thin cracks and added heat, imitating conditions near deep-sea hydrothermal vents. This setup concentrated life-related molecules by up to 1,000 times, making it easier for long molecules like peptides to form. Clays might have played a similar role on early Earth. Another exciting possibility is that simple gases like carbon monoxide, ammonia and carbon could directly form peptides, skipping the need to make amino acids first. One of the biggest unanswered questions in science is how proto-cells, primitive, cell-like structures, first appeared. These simple blobs might have been the first step toward real living cells. A theory called the lipid world hypothesis suggests that the first self-replicating structures were not made of proteins or DNA, but of fat-like molecules called lipids. Lipids can form little bubble-like shapes, especially when shaken in water. On early Earth, these lipids probably didn't look like the phospholipids in modern cells, but they could still form membranes. These bubbles might grow when more lipids are added, and then split into two smaller bubbles, just like living cells divide. These simple membranes might have protected the fragile molecules inside them, such as RNA, and helped start the evolution of more complex life. So far, only a few types of these bubble-forming molecules have been studied, but the number of possible combinations is huge. Some of these early bubbles might have developed a feedback system, where a chemical inside the bubble helped stabilize the membrane, and the membrane helped keep the chemical inside. This feedback loop could be passed on to new bubbles when they split, leading to a kind of evolution. Although no one has yet built a fully working protocell in the lab as of 2014, scientists believe that self-assembled vesicles, those lipid bubbles, were essential parts of early life. According to thermodynamics, life needs a boundary that keeps order inside while chaos stays outside. That's what membranes did. Researchers like Irene Chen and Jack Sostak have suggested that even the simplest proteels could show early signs of competition, energy storage, and reproduction. If a bubble had a stronger, more stable membrane, it might survive better, leading to natural selection even at this primitive stage. Other studies show that fatty acid vesicles can be made more stable with chemicals called isoprenoids, produced in the same Formose reaction that makes sugars. These differences might explain why the cell membranes of archaea and bacteria, two of the oldest life forms, look so different today. Even pressure deep within the Earth could have helped protocells evolve. In tectonic fault zones, pressure cycles, rising and falling again and again, can create and break apart vesicles. In this environment, random chains of amino acids form, and only the ones that help vesicles survive get selected. Over time, these molecules may have become more like real proteins, helping the protocells live longer and reproduce better. For life to begin and grow, something remarkable has to happen. Molecules, which are usually scattered and disorganized, have to come together and arrange themselves in very specific and orderly ways to form living matter. This process involves a decrease in something scientists call entropy, which is just a fancy term for disorder or randomness. In other words, life needs order to exist. But doesn't this go against the second law of thermodynamics? That law says that overall disorder in the universe must always increase. Surprisingly, the answer is no. A living organism might become more ordered, but it does so by creating even more disorder in its surroundings. For example, a cell builds its complex structures, but in the process it also produces heat and waste, increasing the entropy around it. So the rule still holds. It's just that life creates pockets of order within a larger system that's becoming more chaotic. When Earth was still young, billions of years ago, it offered many different sources of energy that could power chemical reactions. One common source was the heat coming from inside the Earth itself, especially around hydrothermal vents, hot openings on the seafloor. But there were other sources too. Sunlight shining down from above, bolts of lightning crackling through the early atmosphere, tiny meteorites entering the sky and burning up, and even bubbles collapsing under the pressure of crashing ocean waves. These forms of energy were more than enough to get early chemistry going, and scientists have proven this through laboratory experiments and computer simulations. Some chemical reactions, though, don't happen easily on their own. But nature has clever ways of making them work, by coupling them with reactions that release lots of energy. A good example of this is iron-sulfur chemistry, which likely played a big role in forming carbon-based molecules on early Earth. One important reaction is the combination of carbon dioxide and hydrogen sulfide on iron-sulfur surfaces. This can take place in water with a neutral pH and at temperatures around 100 degrees Celsius. Around hydrothermal vents, these iron-sulfur surfaces were common, and they could have helped produce small amounts of important building blocks like amino acids and other organic compounds. In the year 1961, a British biochemist named Peter Mitchell came up with a bold new idea called chemiosmosis. He proposed that cells use this method to convert energy efficiently, and today we know that it's used by almost all living organisms, from tiny microbes to complex creatures like us. In our own cells, small structures called mitochondria use this same system to make adenosine triphosphate, or ATP, which is often called the energy currency of life. ATP powers everything from making new molecules to moving parts of the cell. ATP is created by a special protein machine called ATP synthase, which sits on a membrane inside the mitochondria. This machine works because protons, tiny positively charged particles, flow across the membrane, creating a kind of electrical pressure called a gradient. In modern cells, the proton flow is carefully controlled by pumps. But in the earliest life forms, this gradient might have come naturally, from the differences in chemistry between hot hydrothermal fluids and cold seawater, or from certain naturally occurring compounds called quinones that may have helped form early cell-like membranes, especially if life began on land rather than in the sea. Another fascinating idea about the origin of life is known as the PAH world hypothesis. PAH stands for polycyclic aromatic hydrocarbons, a family of molecules that are found all over the universe, in the dust between stars, in comets, and possibly in the chemical soup that covered the early Earth. According to this hypothesis, PAHs may have helped build the very first RNA molecules, which are thought to have played a key role in the beginning of life. Although this idea is still speculative and has not yet been proven, it remains a promising avenue of research. The RNA world hypothesis suggests that, long before DNA and proteins came into the picture, life may have started with just RNA. RNA is a molecule that can both store genetic information and carry out chemical reactions, which means it can act like both genes and enzymes. Many scientists believe that there must have been a time in Earth's distant past when life was entirely based on RNA. However, it's also possible that something else existed before RNA. One version of this idea goes back to Charles Darwin, who imagined that life might have started in a warm little pond. In this version, wet and dry cycles, perhaps caused by rain and evaporation, could have helped molecules concentrate, react, and evolve. Some scientists even propose that there were more than 30 key chemical steps involving RNA alone before the appearance of the last universal common ancestor, Lucer, which is the ancient ancestor shared by all life. This timeline doesn't even include other important processes like the creation of ATP, the Krebs cycle, or the electron transport chain, which are all central to modern metabolism. RNA plays a starring role in today's biology. It helps translate genetic information into proteins, which are the workhorses of life. Small RNA molecules can also speed up important chemical reactions, and the ingredients that make up RNA can be made fairly easily under early Earth conditions. One piece of evidence that strongly supports the RNA world hypothesis is the structure of the ribosome, the machine inside cells that makes proteins. At its core, the ribosome is made entirely of RNA, with no protein parts anywhere near the chemical site that links amino acids together. This strongly suggests that the ribosome, and life itself, began with RNA. The idea of an RNA-based world was first put forward by Alexander Rich in the year 1962, and the term RNA world was coined by Walter Gilbert in 1986. At first, it seemed difficult to explain how RNA's building blocks, called nucleotides, could have formed naturally. In particular, making cytosine and uracil, two of RNA's components, seemed especially hard. But more recent research has found ways they could form. For example, heating a substance called formamide in the presence of certain earth minerals can produce all 4 RNA building blocks, as well as other useful molecules. What makes RNA so powerful is its ability to act as both code and catalyst. For example, an RNA molecule known as RNA replicase can help copy itself, making it autocatalytic, which means it helps speed up its own creation, The scientist Jack Szostak has shown that certain RNA molecules can link together smaller RNA pieces, allowing self-replication. Some experimental RNA systems have even been built where two ribozymes, special RNA enzymes, help make each other. These systems could double in size every hour and even evolve over time, just like life does. If such RNA-based systems existed on early Earth, then natural selection would have kicked in, favouring molecules that copied themselves faster and more accurately. Over time, these autocatalytic molecules could have gained more and more useful abilities. Some of these early RNA systems may have even formed around hydrothermal vents, and an early version of transfer RNA, tRNA, may have been part of the first replicators. Once an RNA molecule could replicate, pass on traits, and vary in function, it would have the three key ingredients for Darwinian evolution: heredity, variation, and differential success. Its ability to survive and reproduce would depend on its structure, its function, and the resources available in its environment. Eventually, life began using proteins, which are even more versatile than RNA. But how did this transition happen? One idea is that short protein-like chains, called peptides, formed and helped RNA do its job more effectively. Scientists believe the earliest ribosomes, the machines that assemble proteins, were probably made entirely of RNA. Later, some of their roles were taken over by proteins. There are still big mysteries left. For example, why did ribosomes evolve in the first place? And how did the genetic code, the system that tells the ribosome which proteins to make, come into being? The scientist Eugene Koonin has pointed out that we still don't have a fully convincing explanation for how life learned to replicate genetic material and translate it into proteins. These two processes, replication and translation, are absolutely central to life, and probably existed before biological evolution could even get started. While the RNA world idea is our best shot at solving this puzzle, it still doesn't fully explain how an efficient RNA replicase or a complete translation system came into being. A technosignature, sometimes called a technomarker, is any kind of evidence that scientists can measure which suggests the existence of technology, whether it's from the past or present. This could be a sign of intelligent life beyond Earth. Technosignatures are a lot like biosignatures, which are clues that life, intelligent or not, exists or once existed somewhere. Some scientists have argued that we should not count radio signals as technosignatures, but this view is not very common. In fact, the well-known astronomer Jill Tarter, a leader in the search for alien life, has suggested that we rename SETI, the search for extraterrestrial intelligence, to the search for technosignatures to better reflect what we are really looking for: signs of alien technology. There are many types of technosignatures that scientists think we might be able to detect with very powerful telescopes, sometimes called hypertelescopes. These include things like radiation leaking from enormous space structures such as Dyson spheres, light from an entire planet-wide city called an ecumenopolis, and massive engines like Shkadov thrusters, which could move stars around the galaxy. All of these things, if they exist, could be detected from Earth if we use the right instruments. In February of the year 2023, after scanning the skies and observing 820 stars, astronomers found 8 possible technosignatures worth studying more closely. One of the most famous ideas is the Dyson sphere, a hypothetical structure that an advanced civilization might build around a star like our Sun. This structure would collect the star's energy and would cause the star to give off a lot more infrared light than normal. This idea was first explored by Freeman Dyson, who wrote a scientific paper in 1960 titled Search for Artificial Stellar Sources of Infrared Radiation. Because of this, SETI researchers have searched for stars with extra infrared light, thinking that could be a sign of a Dyson sphere. Since the year 2005, the Fermilab Research Centre has been conducting a long-term project using data from the Infrared Astronomical Satellite to look for stars with unusual amounts of infrared radiation. So far, Fermilab has identified 17 mysterious sources of infrared light. 4 of these have been described as amusing but still questionable, meaning they're interesting but not yet convincing proof of alien technology. Other astronomers have found more possible candidates in similar searches, but none have been confirmed as true Dyson spheres. In October of the year 2012, well-known astronomer Jeff Marcy, a pioneer in discovering planets beyond our solar system, received a grant to analyse data from the Kepler Space Telescope to look for signs of Dyson spheres. Another fascinating idea is the Shkadov thruster. This is a giant space engine that could theoretically be used to move a star from one place to another, perhaps to avoid dangerous regions of space like cold, molecular clouds or comet-filled zones. These engines would create a strange pattern of dimming when passing in front of a star, different from how planets normally block starlight. If we saw such a pattern, it might be a sign of alien engineering. There are also other clues we might look for. For example, mining activities on asteroids outside our solar system could leave behind detectable traces. Aliens might hide messages in how planets pass in front of stars, or even use lasers to deliberately reveal their presence. Planets could be arranged in mathematical patterns, such as orbits that follow prime numbers, which would be very unusual and unlikely to occur naturally. Stars might show strange activity in their outer layers, like their coronae or chromospheres, which could have been altered by advanced technology. Alien civilizations might even travel through space using free-floating planets, also called rogue planets, which could leave behind other unusual signals. One study has even suggested that if extraterrestrial beings exist, they may have already built networks of communication probes across the galaxy, including possibly right here in our solar system. These probes could detect signals from young planets like Earth and send information back to a home base. According to scientist John Gertz, there might be two types of alien probes: small flyby scouts that come and go, and larger stationary probes that monitor a planet and communicate using specific triggers, like detecting radio waves or signs of life. He also suggested ways we might be able to spot these local alien probes, such as by catching flashes of optical light they might be sending. Gertz also argued that the usual SETI method, waiting to catch a direct signal from far away, might not work if aliens are using interstellar networks made up of communication nodes placed just under a light year apart. These nodes might use pulsars as beacons or modulate their beams in ways we could potentially detect. According to some studies, our past searches wouldn't have been able to find these signals, especially if the aliens were using cost-effective methods we haven't thought of yet. Astronomers like Avi Loeb from Harvard, Edwin Turner from Princeton, and Thomas Beatty from the University of Wisconsin have all suggested that we might also look for artificial light coming from alien cities, such as lights from buildings, factories, or transportation systems. However, it's important to be cautious. For example, NASA's Black Marble experiment in the year 2012 showed that natural fires in places like Western Australia can give off strong and stable light that may look artificial but isn't caused by people at all. To tell the difference between natural and artificial light, scientists use spectroscopy, a method that breaks light into its component colours. Artificial lights, like sodium street lamps, produce very specific colours that stand out and can be identified by future space telescopes. One proposed telescope, called the Large Ultraviolet Optical Infrared Surveyor, could detect lights on Proxima b, a planet around the star Proxima Centauri, if they were about 12 times brighter than Earth's cities, and if we observed the planet for around 300 hours. Another promising idea is to study the atmospheres of planets. We already do this for some planets in our solar system, and for several large hot planets around other stars. If we found gases like nitrogen dioxide or chlorofluorocarbons in a planet's atmosphere, gases produced by human technology on Earth, it might point to the presence of an advanced civilization. This approach is sometimes called atmospheric CT. However, we must be careful. For example, Titan, one of Saturn's moons, has an atmosphere filled with complex chemicals that look like industrial pollutants, but they occur naturally without any life or technology involved. Some researchers think that we should also look for signs of planetary engineering, where alien civilizations might have changed a planet's atmosphere to make it more comfortable for life. If a highly advanced civilization were to build spacecraft capable of traveling between the stars, those vessels might not be completely hidden from our view. In fact, such interstellar spacecraft could possibly be spotted from hundreds or even thousands of light years away. How? Through the unusual types of radiation they might release. For example, a rocket powered by antimatter would shine by emitting specific light particles called photons, and a magnetic sail gliding through the thin gas and dust between stars could produce a unique type of radiation called cyclotron radiation. These signals would look nothing like anything created by nature, making them strong clues that intelligent life exists elsewhere in the universe. Closer to home, inside our own solar system, much smaller probes, sometimes imagined as Bracewell probes, could be hiding. These robotic messengers might have been sent by aliens long ago to quietly observe us. Scientists think they might be detected using telescopes that look for visible light or radio signals. And if aliens had built self-replicating spacecraft, machines that can make copies of themselves, those too might leave signs behind, whether in our own solar system or in the nearby systems of other stars. These signs might include strange devices orbiting the Earth, odd objects on the Moon, or even strange things right here on our own planet. One less far-fetched idea, which involves technology only a little more advanced than what humanity already has, is the concept of a Clark exobelt. This idea was proposed by astrophysicist Hector Socas Navarro from the Institute of Astrophysics of the Canary Islands. Imagine a ring or belt made up of many artificial satellites orbiting an alien planet, similar to the way Earth's geostationary satellites circle above the equator. If such a belt was especially crowded, early simulations suggested it might show up in the dimming patterns, or light curves, we see when an alien planet passes in front of its star. That means we might be able to detect it with telescopes we already have. However, later studies cast doubt on this idea, suggesting such belts would likely be very rare and hard to detect with today's technology. Some scientists believe that if extraterrestrials ever reached a new home somewhere in the universe, they would almost certainly leave behind signs of technology. After all, they would have used advanced tools and machines to make the journey. Over time, they might also create a new biosphere, a whole new network of living things shaped by their presence. There's even a suggestion that alien DNA, particularly from microorganisms, could be used to send self-replicating messages across space. Another potential clue? Solar panels or other artificial surfaces might reflect or absorb light in very different ways from natural materials like ice or rock. These differences could show up in our telescopes, though telling apart a giant alien structure from something like a shiny polar ice cap could be tricky. One of the first serious efforts to find alien megastructures, like Dyson spheres, which are hypothetical objects built to capture energy from a star, was made in the year 1985 by Vyacheslav Slish from the Russian Space Research Institute in Moscow. He used data from the Infrared Astronomical Satellite, or IRAS. Around the year 2001, another search looked at data from the Compton Gamma Ray Observatory, hoping to find traces of antimatter, another sign of artificial activity. Apart from one mysterious signal, which probably had nothing to do with aliens, the search found nothing unusual. In the year 2005, the Fermi National Accelerator Laboratory, Fermilab, began its own survey using the IRAS data. They found 17 objects that looked somewhat strange. Out of those, 4 were labelled as amusing but still questionable, meaning they were interesting but probably not alien in origin. Other searchers have also found odd candidates, but none have yet been confirmed. That same year, scientist Luke Arnold published a paper suggesting that very large, planet-sized artificial objects might be spotted because of the unusual way they would block starlight during a transit. He showed that space missions like CoROT and Kepler, which search for planets by observing how stars dim, could also detect these techno signatures. This method is still considered promising for future space missions. In the year 2012, astronomer Jason Wright and 2 colleagues launched a 2-year project to search for Dyson spheres. They were supported by funding from the Templeton Foundation. The following year, in 2013, astronomer Jeff Marcy received funding to use data from the Kepler Space Telescope to look for both Dyson spheres and possible interstellar communication using lasers. Around the same time, Lucian Wolkowicz also received funding to search for artificial signals in starlight patterns. Beginning in the year 2016, astronomer Jean-Luc Margot at the University of California, Los Angeles started scanning the skies with large radio telescopes in search of techno signatures. That same year, another fascinating idea emerged. What if some stars that seem to vanish from the sky are actually signs of alien technology? A small pilot project was launched and found one mysterious disappearing object. Then, in the year 2019, a larger effort called the Vanishing and Appearing Sources During a Century of Observations, VASCO, project, began hunting for more such disappearing and reappearing stars, as well as other mysterious celestial events. Out of just 15% of the images examined, the team identified 100 strange red transients, brief flashes of light that likely had natural explanations. In the year 2020, the VASCO project launched a citizen science program where students, teachers, and amateur astronomers, especially in Africa, helped examine thousands of images to look for anomalies. VASCO has been called one of the most wide-ranging searches for alien artifacts ever attempted. In the year 2021, Beatriz Villarroel, the project's lead scientist, received a L'Oréal UNESCO Prize in Sweden for her groundbreaking work. Also in June of 2021, the VASCO team announced a strange finding: 9 light sources that had appeared and disappeared at the same time in photographs taken back in the year 1950. They also discovered 3 stars, each of 16th magnitude brightness, that had vanished within just 1 hour on the night of July 19, 1952. In June of 2020, the United States Space Agency NASA awarded its first research grant in over 30 years specifically for the search for alien Techno signatures. This grant helped create an online library to catalogue possible Techno signatures and supported the search for signs of advanced alien civilizations beyond just radio waves. A scientific workshop called Techno Climbs, held in the year 2020, reviewed the best ways to search for these Techno signatures. The workshop also explored how close humans are to creating similar technologies themselves and why looking for alien tools and artifacts, especially inside our solar system, might be worthwhile. In the year 2021, astronomers proposed a checklist to verify narrow-band signals, very specific radio signals that could indicate alien technology. This came after one candidate signal, called BLC-1, was discovered to be likely caused by interference from Earth. Some scientists believe that building observatories on the Moon might greatly improve our chances of detecting alien technology. By the year 2022, scientists had published a detailed overview of many space missions, past, current and future, that might be capable of discovering technosignatures. The Fermi paradox is one of the most fascinating puzzles in science and astronomy. It's about a strange contradiction, something that just doesn't seem to add up. On one hand, it looks like the chances of intelligent life existing somewhere else in the universe are extremely high. On the other hand, we have no clear or confirmed evidence that such life actually exists. This gap between what we expect to see and what we actually observe is what makes it a paradox. Let's put it simply. The universe is unimaginably big, filled with countless stars and planets. Many of these stars are similar to our own Sun, and around many of these stars there are planets that seem a lot like Earth, places that could, in theory, support life. So if the universe is so full of potential homes for life, why haven't we seen any signs of aliens yet? Why is the universe so silent? This big question is what the Fermi paradox is all about. This cosmic riddle is named after a brilliant physicist named Enrico Fermi, who was born in the year 1901 and passed away in 1954. He was one of the greatest minds of the 20th century, a Nobel Prize winner who helped create the first nuclear reactor and played a big role in the development of atomic energy during the Manhattan Project. Fermi had a habit of asking deep and clever questions that made people think hard. One of these questions came up during a casual lunch in the summer of 1950. Fermi was visiting the Los Alamos National Laboratory in New Mexico. While walking to lunch at the Fuller Lodge, he was chatting with his fellow scientists Emil Konopinski, Edward Teller and Herbert York about a strange topic: flying saucers and the possibility of travelling faster than light. Suddenly, in the middle of the conversation, Fermi blurted out a simple but powerful question. He said something like, "Where is everybody?" That single question stunned everyone at the table. Even though it came out of nowhere, everyone immediately understood that he was talking about intelligent life in the universe. If alien civilizations were out there, and especially if some were more advanced than us, shouldn't they have contacted us by now? Shouldn't we have seen some trace of them? According to Herbert York, Fermi didn't stop with just a question. He went on to do some quick mental calculations, classic Fermi style. He estimated things like how many Earth-like planets there might be in the universe, how likely it is for life to begin on such planets, how often intelligent life might evolve, how long advanced civilizations might survive, and how far their technology could take them across space. After thinking through all of that, Fermi reached a surprising conclusion. We should have been visited by extraterrestrial beings long ago, perhaps even many times. But as Edward Teller remembered it, Fermi also said that maybe the distances in space are just too vast. Perhaps Earth is located in a remote neighbourhood of the galaxy, far away from the busy regions where other civilizations might live. Maybe we're out in the cosmic countryside, far from the galactic cities. Even though this paradox carries Fermi's name, he wasn't the first to wonder about the silence of the universe. As far back as the year 1686, a French thinker named Bernard Le Bovier de Fontenelle wrote a book called Conversations on the Plurality of Worlds. In it, he suggested that intelligent beings might exist on other celestial bodies like the moon. But then he introduced a skeptical character in the dialogue, who pointed out that if moon people really existed, they should have come to visit us already. That's one of the earliest versions of the same basic question. Why haven't we seen anyone else? Nearly 2 centuries later, in the year 1865, the famous author Jules Verne explored the idea again in his novel Around the Moon. He too imagined the possibility of other intelligent beings, and his story hinted at the same kind of puzzle. Why haven't they contacted us? In the 1930s, a Russian scientist named Konstantin Tsiolkovsky, who was often called one of the fathers of rocket science, also wrestled with this issue. Although his technical work in rocketry was celebrated by the Soviet Union, his more philosophical writings were largely ignored during the 20th century. In those writings, he asked why we haven't seen aliens if they exist. He proposed an answer. Perhaps alien civilizations are deliberately avoiding us so that we can grow and develop on our own. This idea is similar to something called the zoo hypothesis, which was formally introduced decades later by astronomer John Ball. According to this theory, aliens are watching us the way humans watch animals in a zoo, without disturbing us. Over the years, scientists, philosophers, and science fiction writers have suggested many possible answers to the Fermi paradox. Here are some of the most discussed ideas. Intelligent life might be very rare. Even if simple life is common, intelligent civilizations might be extremely rare or may never emerge at all. Civilizations might not last long. Maybe intelligent species tend to destroy themselves with war, environmental damage, or uncontrolled technology before they can explore space. They might be out there, but we're not looking the right way. Perhaps alien signals are coming in forms we don't yet understand or know how to detect. They might be deliberately hiding. Advanced civilizations might use stealth technology, avoid contact, or follow a strict non-interference policy. We may be too early. It's possible that humanity is one of the first intelligent civilizations in the galaxy, and others haven't emerged yet. They may already be here, but we don't recognize them. Some suggest alien life could be so different from us that we wouldn't even realize it if we saw it. Several scientific facts make this mystery even harder to ignore. There are hundreds of billions of stars in our galaxy, the Milky Way, many of which are similar to our Sun. A large number of these stars likely have planets that are just the right distance to support life, within the so-called habitable zone. Many of these stars are much older than our Sun, which means life had more time to evolve on their planets. If life developed on some of these planets, and if it evolved intelligence, then some of these civilizations might have learned to travel between the stars. Even if interstellar travel is very slow, a determined civilization could explore the entire galaxy in just a few million years, a short time compared to the galaxy's age of over 10 billion years. The famous mystery now known as the Fermi paradox first quietly appeared in a footnote of a scientific paper published in the year 1963 by the astronomer and science communicator Carl Sagan. Just 2 years later, in 1965, researcher Stephen Dole spoke at a scientific meeting and raised a striking question. If there are so many advanced forms of life out there in the universe, then why haven't we seen any of them? This puzzling question caught people's attention, though interestingly, Dole didn't mention Enrico Fermi by name. even though the mystery would eventually be linked to him. Soon after, in a book titled Intelligent Life in the Universe, written by Carl Sagan and the Soviet astrophysicist Iosif Shklovsky, a chapter carried the simple but powerful question attributed to Fermi: where are they? This question started becoming a central theme in discussions about alien life. As the years passed, the mystery gained more attention. It showed up in NASA's Project Cyclops report in the year 1970, which explored ways to search for extraterrestrial intelligence. It was mentioned again in a 1973 book by Carl Sagan, and once more in a 1975 article written by David Viewing in the Journal of the British Interplanetary Society. This article was especially important because it was the first time someone called this mystery a paradox. Later in 1975, another scientist, Michael Hart, published a much deeper and more detailed examination of this mystery in a journal called the Quarterly Journal of the Royal Astronomical Society. Hart took the issue seriously. After carefully thinking through all the possibilities, he boldly concluded that we are the first civilization in our galaxy. In his paper, he suggested that there are 4 main reasons why we might not see alien civilizations, even if they exist. These reasons fell into 4 broad groups: physical limitations, maybe space travel is just too hard, even for advanced aliens; sociological choices, maybe aliens know we're here, but they deliberately choose not to come; timing, maybe they just haven't gotten around to visiting Earth yet, they already came, maybe they visited a long time ago, and we missed it or forgot. Hart's paper created quite a stir. It didn't just interest scientists, it even reached the halls of government. The topic was discussed in the House of Lords, the upper chamber of the United Kingdom's Parliament. In response to Hart's bold claims, another scientist named Frank Tipler wrote a paper titled "Extraterrestrial Intelligent Beings Do Not Exist." Tipler argued that if an intelligent alien species had really existed somewhere in the universe, they would likely have developed self-replicating spacecraft, machines that could build copies of themselves and spread through the stars. These machines would have reached the solar system by now, he said, and we would have seen them. Since we haven't, Tipler concluded, intelligent aliens probably just don't exist. Then, in the year 1977, the actual phrase Fermi paradox was coined by David Stevenson in an article. From that point on, the term became widely used. However, the growing popularity of the Fermi paradox actually had a negative side. It cast a shadow over efforts to search for alien life. In the year 1981, Senator William Proxmire referred to Tipler's argument when he helped put an end to NASA's SETI program, which was a federally funded project aimed at searching for signals from alien civilizations. The scientist Robert Gray later argued that the Fermi paradox may have created an unofficial block on government support for certain kinds of research in astrobiology, which is the scientific study of life in the universe. Interestingly, Enrico Fermi, the man after whom the paradox is named, never actually wrote or published anything about it. Carl Sagan even once suggested that the famous quote might be more legend than fact. Some scientists have criticized calling it the Fermi paradox at all, suggesting that names like the Hart-Tipler argument or the Tsiolkovsky-Fermi viewing Hart paradox would be more accurate. According to Robert Gray, many people have misunderstood what Fermi actually meant. He wasn't asking why aliens don't exist. He was questioning whether long-distance space travel is truly possible. Another researcher, Robert Freitas, also criticized the logic behind the paradox, reminding people that absence of evidence is not evidence of absence. Just because we haven't found aliens doesn't mean they aren't out there. At its core, the Fermi paradox highlights a deep contradiction. The universe is enormous, with countless stars and likely even more planets, and yet we have no solid proof that any intelligent life exists anywhere other than Earth. The paradox comes from 2 main ideas. Let's look at the numbers. Our home galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. The entire observable universe contains an estimated 70 sextillion stars. That's the number 7 followed by 22 zeros. Now, even if intelligent life only appears on a tiny fraction of planets orbiting these stars, we should still expect to see a large number of civilizations out there. This assumption is based on something called the mediocrity principle. That principle says Earth is probably not special. It's an average planet, not a rare exception. So if life arose here, it should also arise elsewhere, many times over. The second idea is based on the behavior of intelligent life. Once a species becomes advanced enough, it can overcome limits like food shortages or environmental problems. It might then spread into space, seeking out new worlds to live on and resources to use. Even if only a few alien civilizations followed this path, they could have colonized their home star system and possibly even neighboring systems. So, if intelligent life is out there and capable of expanding, why don't we see any evidence of it? On Earth, in our solar system, or anywhere else in the observable universe? After all, the universe has been around for about 13.8 billion years, and many stars are billions of years older than our Sun. That's plenty of time for civilizations to rise and spread across the galaxy. And yet, there's silence. That's the heart of the paradox. There are many possible explanations. Maybe intelligent life is much rarer than we think. Maybe our ideas about how aliens behave are just wrong. Or maybe we still don't understand the universe well enough to even ask the right questions. The Fermi paradox can actually be asked in two different ways. Version 1, where are they? This version asks, why haven't we found any aliens or their technology in our solar system? If travelling between stars is possible, even at speeds slower than what Earth's technology might soon achieve, it would still take only about 5 million to 50 million years to explore or colonize the entire galaxy. That may sound like a long time to us, but it's incredibly short when you consider the age of stars and planets. Since the Milky Way is full of stars much older than the Sun, it's logical to ask, if intelligent life evolved on one of those older worlds, why haven't they explored or colonized the galaxy already? Even if they didn't want to colonize, they could have sent robotic probes to explore, some of which should have left behind visible traces, such as spacecraft wreckage, mining scars on asteroids or signals, but we haven't seen any of that. Version 2. Why is the universe so quiet? This version doesn't assume that aliens are travelling between stars. Instead, it asks why we don't see any signs of intelligent life anywhere, not even in other galaxies. Sure, distant galaxies are unimaginably far away, and even alien civilizations might not be able to travel to us from there. But if any of them were highly advanced, they might still be visible from far away. In theory, they could build huge structures or use vast amounts of energy, creating signals that we could detect here on Earth. And given the size of the universe and the long span of time involved, we should expect some of them to exist somewhere and be detectable by now. But again, we don't see anything. Some scientists aren't sure whether this puzzle is more troubling when we look at just the Milky Way galaxy, or when we consider the entire observable universe. Either way, the silence remains one of the biggest mysteries of modern science. The Great Filter Theory is a powerful idea first proposed by researcher Robin Hanson in the year 1996. It describes any natural obstacle that might make it extremely rare, or nearly impossible, for simple, lifeless matter to eventually turn into a technologically advanced civilization capable of space travel or communication across the stars. In simple terms, it's the name for whatever mysterious step, or steps, in the journey from chemicals to intelligent beings might be so difficult that hardly any civilization ever makes it. Among all the steps in this journey, the one that scientists most often agree could be the hardest is something called abiogenesis. That is, the moment life first emerges from non-living materials. It likely happened very slowly, with molecules becoming more and more complex over time until some of them began to make copies of themselves. This would have happened through random chemical reactions and taken an incredibly long time. Other candidates for great filter events include the appearance of eukaryotic cells. These are the complex cells that make up plants and animals, or the development of meiosis, which is the special kind of cell division used for reproduction. Some scientists also believe that the hardest step might be the evolution of a brain advanced enough to think logically and solve problems. Two astrobiologists, Dirk Schulze-McCouch and William Baines, looked closely at the history of life on Earth and focused on events like convergent evolution, where similar features evolve independently. They concluded that many key transitions, such as oxygen-producing photosynthesis, the rise of eukaryotic cells, the appearance of multicellular organisms, and even the development of tool-using intelligence, are likely to happen on any Earth-like planet if given enough time. But even with this optimistic view, they still suggested that the Great Filter could be one of the following: the beginning of life itself, Abiogenesis, the leap to human-like intelligence, or the inability to expand to other planets, perhaps due to self-destruction, war, or running out of needed resources. Another scientist, paleobiologist Olev Vin, believes that the Great Filter might be tied to something even more basic: universal patterns in how animals behave and evolve. If he's right, then the same evolutionary roadblocks may stop intelligent life from progressing, no matter where it evolves. In the year 2021, Robin Hanson and his colleagues introduced a new set of ideas about aliens that could help explain why we have not found any. They spoke of quiet, loud, and grabby aliens. Quiet aliens would be those that exist, but keep a low profile and are either hard or impossible to detect before they vanish. Loud aliens, on the other hand, would spread across the universe in an obvious energetic way, changing galaxies, building megastructures, or doing things we could easily see with telescopes. Grabby aliens would go even further. They would expand so quickly, close to the speed of light, that they would prevent other civilizations from emerging in the regions they reach. According to this theory, if loud and grabby aliens were common, we should have noticed them by now. But we haven't. That suggests they are very rare, and if they are rare, then quiet aliens are probably rare too. Hansen and his team also suggested that humanity is still in the early stages of its possible development. If we were further along, we might already be the kind of species that other civilizations could detect. But since we aren't, and we don't see others, it means we're likely still at the beginning of a long journey. Back in the year 2013, scientists Anders Sandberg and Stuart Armstrong explored how intelligent life, if it had the right energy and tools, could spread not just through the Milky Way, but even to other galaxies. They estimated that it might take just a few million years, which is very short compared to the age of the universe, for a civilization to colonize an entire galaxy. Reaching nearby galaxies would not be much harder than crossing the distances between stars. They argued that since this kind of expansion seems possible, the fact that we haven't seen any signs of it makes the Fermi paradox even more puzzling. This paradox has two main parts, both backed by real evidence. First, we now know that there are many planets out there that could support life. This was only a guess back when Enrico Fermi first asked, "Where is everybody?" But now we have proof. Thanks to modern space telescopes, we've discovered thousands of exoplanets, and scientists believe there could be billions of habitable worlds in just our galaxy alone. The second part of the paradox is that, even though the universe seems full of potential homes for life, we still have no solid evidence that aliens exist. This has led to serious scientific efforts to search for life, both simple and intelligent. These efforts began around the year 1960 and are still continuing today. Sometimes astronomers see strange things in space that are hard to explain. For example, when pulsars were first discovered in the year 1967, their perfectly regular signals led some scientists to jokingly call them little green men, because they thought aliens might be sending signals. Eventually, natural explanations were found for all such discoveries, but scientists remain alert to the possibility that truly unusual signals could point to something artificial or intelligent. Some proposed signs of alien activity include asteroid mining, which could change the look of dusty disks around stars, or unusual light patterns caused by dumping nuclear waste into stars. Another possible sign would be radio waves. Building a radio telescope and sending or leaking signals into space is considered a likely step for any advanced species. For example, any aliens observing our solar system might notice strange, intense radio waves coming from Earth, caused by our TV stations, radar, and telecommunication systems. These signals might not be meant for others, but they could still be detectable. However, it's unclear how far such signals can travel. As of the year 2019, even the most powerful radio telescopes on Earth could not detect Earth-like radio broadcasts from more than a fraction of a light year away. Still, an advanced alien civilization might have far better equipment than we do. Groups like the CT Institute and Breakthrough Listen have spent decades scanning the skies for any radio signals that look artificial, ones that repeat in strange ways or are too bright to be natural. So far, they haven't found anything that clearly points to alien intelligence. Meanwhile, the search for planets outside our solar system is one of the most exciting areas in astronomy. The first possible Earth-like planet found in a habitable zone, a region around a star where liquid water might exist, was discovered in the year 2007. Since then, space missions like Kepler and TIAS have been working hard to detect and study small rocky planets like Earth. These efforts are helping scientists estimate just how many such habitable planets may exist, and perhaps how many could one day be home to intelligent life. In the year 1959, a brilliant physicist named Freeman Dyson noticed something interesting about the way civilizations grow. He saw that as human societies become more advanced, they tend to use more and more energy. Based on this idea, he imagined what an incredibly advanced civilization might do to meet its growing energy needs. Dyson proposed that such a civilization might try to collect almost all the energy from its star, not just a little bit, like we do with solar panels on Earth, but nearly everything. To do this, he suggested a fascinating concept, a Dyson sphere. This wouldn't be a solid shell like a giant ball around the star. Instead, it might be made of countless orbiting satellites, mirrors, or solar collectors forming a huge cloud or shell around the star. These structures would gather the star's light and turn it into usable energy. Such a huge engineering project is called astroengineering, building things on a scale that involves stars and planets. Now, if a star were surrounded by a Dyson sphere, it would no longer shine the same way. The star's natural light, which scientists can study using special tools called spectrometers, would be changed. Instead of the normal light pattern that comes from a star's atmosphere, the star would glow more like a black object that's being heated, what physicists call black body radiation. This type of light tends to shine most strongly in the infrared part of the spectrum, which is invisible to our eyes but detectable with special instruments. Dyson suggested that if we looked at the light coming from distant stars and saw this unusual pattern, we might be seeing signs of an advanced alien civilization harvesting its star's energy. Over the years, scientists have searched for stars that might show signs of being surrounded by Dyson spheres. Thousands of galaxies have been carefully observed. So far, no one has found any clear evidence that any stars are being artificially enclosed or altered. However, in October of the year 2015, astronomers noticed something odd happening with a star called KIC 8462852. Using the Kepler Space Telescope, they saw the star's light dimming in strange ways. Some people began to wonder, could this be the work of an alien civilization building a Dyson sphere? Exciting as the idea was, further studies in 2018 showed that the dimming depended on the colour of the light. That pointed to the presence of dust, not a solid object, as the likely cause. So, the mystery faded, and the idea of a Dyson sphere around that star lost support. Some scientists believe that intelligent life in the universe may be extremely rare, maybe even limited to Earth. This belief is part of what's called the rare Earth hypothesis, which goes against the principle of mediocrity, the idea that Earth is just an average planet in an average place in the universe. According to the rare Earth view, many very specific and lucky conditions must come together for complex life to appear. These include being in a galactic habitable zone, the right part of a galaxy where things are calm enough for life to exist, having the right kind of star and planet, including a planet that stays in the habitable zone, neither too hot nor too cold, for billions of years, a giant planet like Jupiter nearby, which protects Earth from deadly asteroids by pulling them in or deflecting them, a large moon, which helps stabilize the planet's tilt and seasons, a magnetic field to shield the surface from harmful cosmic rays, plate tectonics, which help recycle elements and regulate the climate, the right chemistry in the planet's crust, atmosphere and oceans, big events that shake up evolution, such as long periods of freezing, ice ages, or rare impacts from huge space rocks, and perhaps the most mysterious step of all, the transition from simple single-celled organisms, prokaryotes, to more complex ones, eukaryotes, the development of sexual reproduction, and the burst of life during the Cambrian explosion. In his book Wonderful Life, published in the year 1989, scientist Stephen Jay Gould suggested that if we could rewind time to the Cambrian explosion and change just a few things, humans might never have evolved. Other scientists like Ricardo Fontana, Leo Buss, and Stuart Kaufman have argued that life has certain self-organizing properties that might make complexity more likely, but not guaranteed. Even if complex life forms do evolve on other planets, that doesn't mean intelligent life, or civilizations, will follow. Some scientists call this the algae versus alumni problem. We might find signs of life, like plant-like organisms or microbes, but not necessarily signs of graduates with diplomas, or intelligent beings who can build cities and use technology. Astronomer Charles Lineweaver has pointed out that traits like large brains are not guaranteed to evolve. They are not more likely than odd features like the long noses of elephants or aardvarks. As he said, dolphins have had about 20 million years to invent radio telescopes, but they haven't. Science writer Rebecca Boyle also noted that out of the many millions of species that have ever existed on Earth, only one species, humans, has become spacefaring, and even we are just beginning to explore space. It's also possible that many young civilizations might go extinct before they get the chance to explore space or communicate with others. Planets can heat up too much or cool down too fast. On Earth, life has nearly been wiped out multiple times. The most famous event was when the non-avian dinosaurs disappeared, most likely due to a massive asteroid impact. Other causes of mass extinction could include giant volcanic eruptions or gamma-ray bursts from distant stars. These kinds of disasters might be common in the universe and could keep destroying intelligent life again and again before it can spread or send out signals. Even so, the risk of total extinction might be low during the life of a full civilization. Scientists have looked at impact craters on both Earth and the Moon and estimated that really huge impacts, big enough to cause global destruction, happen only about once every 100 million years. It's very possible that intelligent alien species do exist somewhere in the universe, but they might still be in the early stages of development. They could be primitive, similar to how humans were thousands or even millions of years ago, and may not yet have developed the tools or technology needed to communicate across space. Just like non-intelligent life, such civilizations would be extremely hard to find or detect from far away. Even if we wanted to visit the nearest stars using the rockets we have today, the journey would take several 100,000 years. That's longer than humans have even had writing, and it shows just how enormous the distances in space really are. Some scientists argue that the lack of contact with aliens may not be so surprising. After all, in the entire history of life on Earth, which stretches back over 3.5 billion years, only one species, humans, has built a civilization advanced enough to create radios and spaceships. That fact alone makes many people think that intelligent spacefaring civilizations might be extremely rare throughout the universe. Two scientists, Amedeo Balbi and Adam Frank, suggest an interesting idea called the oxygen bottleneck. They point out that in order for a civilization to become technological, using fire, smelting metals and building machines, a planet needs to have a high enough level of oxygen in its atmosphere. On Earth today, our atmosphere contains about 21% oxygen, but in the past it was much lower, and on other planets it might be low too. While a little oxygen is enough to support basic life like plants and animals, you need a lot more to allow things like fire and combustion to work. And without fire, a civilization can't begin the path toward industry and technology. So, having a high oxygen level might not just be a sign of life, it might also be a key ingredient for the rise of advanced, detectable civilizations. Another fascinating idea is called the water world hypothesis, proposed by author and scientist David Brin. He explains that Earth might be unusual compared to other habitable planets. Our planet lies near the very inner edge of the so-called Goldilocks zone, the range of distances from a star where liquid water can exist. Brin suggests that Earth has more oxygen and less water than most potentially habitable planets. We have about 32% land mass, which may be a lot compared to planets that are mostly covered in deep oceans. If most life-bearing planets are water worlds with very little land, that would make it harder for creatures like humans, who use hands, build fires and invent tools to evolve. So, if we ever build starships and start exploring the galaxy, we might find many life-filled planets. But most of the intelligent beings there might live in the oceans, creatures like dolphins, whales or squid. These beings could be smart, maybe even smarter than us, but they wouldn't be able to make tools, build cities, or travel through space. And in that case, humans might be the only species in the galaxy capable of building starships, becoming space explorers, and shaping the future of the cosmos. During the time between the 18th and 20th centuries, humanity went through an incredible transformation known as the Industrial Revolution. Scientific and technological progress sped up dramatically compared to earlier times. Many people began to assume that this rapid growth would continue, and that eventually we would reach even higher levels of achievement, like building colonies on other planets. However, some thinkers suggest that there might be a universal limit to technological development, often shortened as ULTD. This means that there could be a ceiling, a maximum level of growth, that no civilization can pass. This limit could be caused by economic difficulties, physical laws, like the fact that travelling faster than light might be impossible, or even the biological limits of the species involved. Another gloomy idea is that once civilizations become advanced enough to use radio waves or explore space, they don't last very long. They might destroy themselves soon after. The astrophysicist Sebastian von Herner suggested that progress on Earth has mostly been driven by two things: the desire to dominate others and the wish to live more comfortably. Sadly, both of these forces can lead to destruction. The first can cause wars, and the second can lead to laziness, decay, or mental decline. There are many ways a civilization might wipe itself out. These include world wars, environmental disasters, dangerous biotechnologies, synthetic or mirror life, running out of essential resources, climate change, or badly designed artificial intelligence. And because our modern world is so connected, one mistake or accident in one place can affect the entire planet. Back in the year 1966, the famous scientists Carl Sagan and Joseph Shklovsky predicted that most advanced civilizations would either destroy themselves within 100 years of gaining the ability to send messages across the stars, or they would somehow learn to control their dangerous tendencies and survive for billions of years. The late physicist Stephen Hawking offered another deep insight. He believed that once civilizations enter what he called the external transmission phase, where creating and sharing knowledge becomes more important than physical evolution, they become unstable. If the system of knowledge grows faster than our ability to control it, disaster may follow. Hawking suggested that humans might need to redesign themselves, possibly by enhancing our brains through machines or rewriting our DNA to become more intelligent and less aggressive. Without such changes, he believed that we might not survive the challenges ahead. He warned that powerful new inventions like super-intelligent AI or antimatter weapons could emerge faster than our governments and societies can handle. If that happens, disorder would grow, and the ability to manage these dangerous tools might collapse. As a result, global societies could fall apart, leading to a total breakdown of civilization. We've seen smaller versions of this idea in real history. One famous example is Easter Island in the Pacific Ocean. Between 1500 years before Christ and around 800 years after, people settled and expanded across many Polynesian islands. But as populations grew, resources ran out, and there were times when entire communities collapsed. There are stories of entire islands where almost all the adult males were killed, sometimes through civil war, and sometimes through invasions from other islands. In the year 2018, a team led by Adam Frank used these examples to explore the idea that civilizations like ours may be doomed by their own energy use. They suggested that when a civilization becomes highly energy intensive, it can actually damage the environment that supports it. Based on physics and mathematical modelling, they showed that this could be a common problem across the universe. In other words, climate change might not be just an Earth problem. It could be a universal problem for any young civilization trying to grow fast. Understanding this could help us see our current environmental crisis from a broader cosmic perspective, and maybe even find a way to avoid collapse. One fascinating and unsettling idea is that whenever an intelligent alien species becomes highly advanced in technology, it might begin to destroy other intelligent life as soon as it detects them. The reason? It could be out of fear, greed, or the desire to dominate space. These attacks might even be carried out by machines, tiny, self-replicating robotic probes that travel across the stars, hunting down potential rivals. This dramatic concept has been explored in science fiction for many years. Author Fred Saberhagen wrote about it in his famous Berserker series. Physicist and writer Gregory Benford also imagined this scenario, as did science fiction authors Greg Bear in The Forge of God and Liu Cixin in his highly acclaimed The Three-Body Problem series. Such destruction might not always come from hatred or hunger for power. Sometimes it could be a cold, calculated decision. In the year 1981, cosmologist Edward Harrison suggested that a wise, long-surviving species, one that has managed to avoid destroying itself, might see any newly rising intelligent life as a potential threat. To them, wiping out a new civilization early might seem like the safest option. After all, humans themselves are super predators on Earth, hunting and dominating almost every other species. So perhaps aliens would act the same way, powerful, aggressive, and determined to remain on top. Another possible explanation is something called the tragedy of the commons, mixed with the idea that humans are just lucky. If one species develops space travel first, it might, without even trying, prevent other civilizations from getting a chance to rise. Maybe humans just happen to be that first species. Even if alien civilizations are out there, we might not notice them because they're only visible for a very short time, especially through radio signals. Most scientists think that once a civilization becomes advanced enough, it moves beyond basic radio waves. Still, there might be other signs of their existence. For example, powerful microwave beams could be used to send energy from solar satellites down to a planet's surface, and these might leak out into space. In a magazine article published in the year 2006, scientist Seth Shostak explained that as civilizations grow more advanced, they tend to hide their communications. On Earth, for instance, we're already switching from traditional broadcast to underground cables and fiber optics. We also now use advanced methods like spread spectrum transmissions, which are harder to detect. This means our planet is getting quieter to anyone listening from space. Going further, it's possible that advanced alien species no longer use any kind of electromagnetic waves to communicate at all. They might use entirely different methods, ways of sending messages that we haven't even invented yet. Some scientists have suggested that they might send signals using particles called neutrinos. These particles can travel through entire planets without being stopped, and as of the year 2009, large neutrino detectors were already being built on Earth for other scientific goals. Maybe, someday, they will catch a signal from deep space. There's another important idea too. Maybe we humans just don't understand aliens well enough. Life on other planets might think in totally different ways. Maybe they are not even interested in contacting us. It's possible that the kind of math we use on Earth makes no sense to them. Some researchers believe that only abstract math might be different, but the math tied to physics should look the same across the universe, even if aliens use different ways to describe it. In his book written in the year 2009, Seth Shostak mentioned that our search for alien life still focuses on beings that early astronomers like Percival Lowell would have imagined, creatures living on planets like Mars. But real aliens might be far stranger. Even the way alien minds work might be beyond our imagination. Carl Sagan once suggested that an alien species might think 1,000,000 times faster or slower than we do. If they sent us a message, we might hear it as nothing more than random noise, simply because our brains aren't wired to understand their speed or timing. Physicist Paul Davies brought up a powerful idea. He said that just a few hundred years ago, people would never have guessed that a machine, like a modern computer, could work just by moving information inside itself. So, what if there are even higher levels of technology that we cannot imagine today? He suggested that alien technology might exist on what he called a third level, or even a fourth or fifth level, realms of operation beyond our current knowledge. These levels might not show up in ways we can detect, and we don't even have the words to describe them yet. But that doesn't mean they're not real. Science fiction legend Arthur C. Clarke once compared our situation to that of jungle tribes listening for the beat of drums, while modern communication buzzes invisibly all around them. In his view, our own technology might seem laughably simple to a highly advanced alien species. Some scientists believe that once civilizations become extremely advanced, they go through a kind of technological singularity, changing so much that they no longer even have physical bodies. They might become post-biological beings, no longer made of flesh and blood, but perhaps of pure energy or digital intelligence. Another theory, suggested by astrophysicist Adam Frank and his colleagues, says that advanced civilizations may not want to colonize every star in the galaxy. Instead, they might adopt a calmer, more balanced way of expanding, one that doesn't lead to endless growth or sudden collapse. A magazine article published in February of the year 2019 put it this way: a single, super-powerful alien empire might sweep across the galaxy, but most civilizations, like our own, are messy, diverse, and far from united. Frank and astronomer Jason Wright ran computer simulations using different settings, like how long a settlement might last, how many planets are suitable for life, and how long it takes to prepare a new launch. They discovered a third possibility. The Milky Way galaxy could be partially settled, and stay that way for millions or even billions of years. Their research showed that we don't need to believe Earth is the only world with intelligent life, just because no aliens have visited us. It's still possible that other civilizations exist, but are expanding slowly, cautiously, or in ways that don't reach us yet. Another interesting idea is that civilizations might only choose to explore new stars when those stars come close enough. The most common stars in our galaxy, small cool ones called K-dwarfs and M-dwarfs, have very long lifespans and are more likely to pass near other star systems. These stars might be the top choice for alien civilizations that want to take their time. Even with a slow interstellar travel ability of just 0.3 light-years at a time, all M-dwarfs in the Milky Way could be visited in about 2 billion years. And if travel extends to 2 full light-years, then every K-dwarf could be reached in the same amount of time. One possible idea that could make the Fermi paradox even more puzzling is the rise of artificial intelligence, AI. If machines one day become more intelligent than the humans who created them, they might take over completely. These super smart machines could then start spreading across the galaxy using self-replicating probes, machines that build copies of themselves and travel from star to star. This kind of expansion could happen much faster than anything biological life could achieve. But here's the twist. It's also possible that after these machines replace their creators, they might choose not to spread through space. Or perhaps they simply don't last very long for various unexpected reasons. A scientist named Michael A. Garrett has offered a troubling thought. He believes that intelligent life forms made of flesh and blood, like us, may often underestimate just how quickly artificial intelligence can grow and improve. By the time they realize what's happening, it might already be too late to do anything about it. This could be part of the so-called Great Filter, the mysterious barrier that prevents civilizations from surviving long enough to spread across the stars. Garrett also suggests that this rapid rise of AI might mean that most advanced civilizations only last for about 200 years after reaching a certain technological stage. That short lifespan could help explain why SETI, the search for extraterrestrial intelligence, continues to hear nothing but silence. Now imagine that it becomes possible to build machines with human-level intelligence, and that these intelligent programs can be sent across vast distances in space and rebuilt on other machines. In this case, travelling across the galaxy in spaceships might no longer make economic sense. Louis K. Scheffer, another scientist, calculated that sending information by radio waves across space could be anywhere from 100 million to 100 quadrillion times cheaper than flying a ship there. For a civilization made entirely of machines, this difference in cost is huge. It would be far more efficient to send messages, essentially computer data, to machines that are already stationed on distant planets or space stations. Once the very first advanced civilization has explored the galaxy, planted its machines across star systems, and figured out the best way to send messages, all the civilizations that come after it might simply send their digital minds to those existing machines. That would be much faster, cheaper, and easier than building brand new spaceships and flying across the stars. But there's a catch. Each star system might only need one of these intelligent machines, and the messages being sent would be carefully directed, using high-frequency signals and the least amount of energy possible to save costs. Because of this, the signals would be extremely hard for us on Earth to detect. They would not be loud or spread out like a broadcast. Instead, they would be more like private whispers across space, too faint and focused for our current technology to pick up. So, even if the galaxy is buzzing with the activity of machine civilizations, we might still see nothing, hear nothing, and continue to wonder, where is everybody?